Okay, now it is. Brief introduction again for those of you who weren't there yesterday. This workshop has been co-organized by the Lighthouse activity and research on climate intervention, and on the Stratospheric Aerosol activity of the WCRP core project on atmospheric processes and their role in climate. A big thank you again to Indumathi and Liwa from the WMO for helping with technical support, and to Mark for doing a lot of the work on organizing this. Mark, do you want to go over the rules?
Yes, thank you, Daniela, and also welcome you on behalf of the Aerosol activity of APAC. And I will be shorter than last night. Last night we had the first session, which went very well and which ended on time, actually. So we aim for the same thing today. So there are some rules that all speakers can see in the webinar chat. I'm pasting that there again. So hopefully you can read it. That's about timekeeping and like under what circumstances we may mute your mic, things like that, and about breaks. And for the audience, please use the Q&A box at the bottom of the screen to ask any questions. And then panelists or speakers can answer them immediately in writing. And some of the interesting, important questions we will pick up and take to the session discussions. That's always around like 5 to 12 minutes, something like that, at the end of each session of talks, each block of talks. And then some of these questions we will also take into the longer discussion blocks we have tomorrow and on Thursday. And then we are preparing ways to continue discussion after the meeting to take the momentum and not lose everyone again and get together. And also for people who don't attend all sessions to be able to discuss and ask questions and debate further if needed. And the WMO team, they will make the recordings of the sessions available to participants as quickly as possible. I send a link in the email where you can find them as soon as they are ready. Sometimes you may have to wait a bit longer. They really try hard to put it there, but please be patient. Okay, with that, I hand back over to Daniela, who will share the first session. And yeah, look forward to an exciting day too.
Okay, so we can get started with the first session. Today's first session is SAI simulations, capabilities, validation, and process parameterization. We have a wide range of talks going all the way for 1 hour, 5 minutes when we'll have a session discussion. So we start with the first talk today being Sebastian Istam. Seb, please take it away.
Thank you. Really appreciate the opportunity to be here. So in brief, I'll be talking about key gaps in models' physical representation of stratospheric aerosol injection and its impacts. This is work that was done under the Geoengineering Modeling Research Consortium as part of a larger effort to understand modeling gaps relevant to multiple forms of solar radiation management. But what I'm going to be doing today is really discussing the work of the Stratospheric Aerosol Working Group. And you can see the names of the working group there. I was just the person who helped to bring this together into the larger paper. So thank you so much for that to that group. So next slide, please. The basic question, of course, common across all forms of SRM, is where models might not be accurately representing the physical response to geoengineering or any form of solar radiation management. Extrapolating from the idea that a computational representation of the Earth is not quite the same as the Earth itself, then that computational representation plus GHGs, of course, isn't going to be quite the same as the real one plus GHGs, and then extrapolating further to what happens when you add stratospheric aerosol to the mix. So with that in mind, it's hard to assess whether the process responses will extrapolate appropriately because we are going outside of, to some extent, our lived experience. Next slide, please. The way that we wanted to come at this was from an expert assessment. So with that in mind, back in 2022 now, we initiated a series of meetings over several months where we tried to bring together working groups, one in stratospheric aerosol, one in cirrus clouds, and one in marine clouds, who would try to identify an exhaustive list of possible gaps. We were then lucky enough to be allowed at the 2023 GeoMet meeting in Exeter to do an in-person assessment, bringing together those working groups with a broader community to assess the degree of agreement or disagreement between the identified gaps and those that were identified during that meeting and in the community, and perform a form of prioritization. So thanks so much again to GeoMIP for hosting us in that. We then performed a series of finalization meetings, again with those online working groups over the following months to condense it into a final list. And this listing has now been published in a commentary in James. Next slide, please. So again, that working group was led by Amy Butler and Simona Tilms, and consisted further of Eva Bednars, Gabriel Kyodo, Daniela Visioni, Lily Jia, and Pengfei Yu. I also wanted to acknowledge Chelsea Thompson at NOAA, who produced the great graphics that we're about to show you that I think really helped us tie together the work of the working groups. Next slide, please. So this graphic, which is in the paper, I think illustrates the three main gaps which the working group prioritized and identified as being prioritized, and which I'll talk through. These three gaps, though, I should mention, are in addition to two cross-method gaps. The first being the need for more observations tailored to these areas, and the second being the need for evaluation of model consistency across scales. Next slide, please. The first stratospheric aerosol-specific gap relates to representing microphysical changes in the stratospheric aerosol layer. In particular, the representation of concentrated plumes in relatively coarse resolution GCMs. They noted that models not only have limited skill in reproducing observed volcanic aerosol distributions, but that those volcanic eruptions are themselves not perfect analogs for the aerosol sources associated with SAI, and even worse analogs for plume scale aerosols. So the suggestion was actually to more incorporate model developers into measurement field campaigns, which could help in identifying what observations are needed. Next slide, please. The second area was uncertainties in modeled aerosol radiation interactions, and in particular, the amount of local heating generated in the stratosphere, the surface response, and potentially changes in tropospheric photolysis. So suggestions in this area were for there to be more line-by-line versus broadband comparisons when it comes to radiative transfer calculations, for multi-model comparisons of radiative properties across many different wavelengths, and for idealized simulations to isolate uncertain processes. Next slide, please. The third and final of the priorities that were identified by the working group was to focus on aerosol chemistry interactions. They noted that the effects of continuous injections on stratospheric and tropospheric chemistry may not be that well characterized in current models, noting that stratospheric aerosol is likely to cause a cumulative effect on both, leading to model disagreement. This includes the absence of some key processes from certain models that might have been well adapted to, say, GHG representation, but not so much SAI. They simply weren't previously critical. Suggestions in this respect were for more observation-based model assessment, if possible, but also for specified dynamic simulations to really assess uncertainties and inaccuracies in chemistry, and also for lab-scale studies to constrain chemical unknowns. Next slide, please. On top of all of these, as one of the takeaways, I want to highlight that the process here really was as valuable as the outcome. And again, just give a huge thank you to both the participants of the working group and to GeoMIP for hosting. But on a hopeful note, I'd say that having gone through several of these priority gaps, they also highlighted that there are actions that can be taken right now that can improve modeling. Some of them are easier in some ways than others, being constrained to modeling world, but in others, there are some difficulties, and that they noted in particular the value of accelerating integration of SAI modeling into observation campaigns and the value thereof. That's it. So thank you so much for this opportunity to speak, and I'm looking forward to the rest of this session.
Thank you, Seb. Perfectly on time. We move on to the next speaker. That's Simone Tilms.
Okay, yeah, thank you very much. Thank you, Seb, for giving a great introduction, basically also to my presentation. I'm talking about uncertainties depending on specifics of the aerosol microphysical model. So one of the key points that were pointed out earlier as an uncertainty, and this is a summary of a paper that we have right now in ACPD in a discussion, and I want to acknowledge my co-authors and others that helped. Next slide. Frank Holch yesterday already pointed out the large uncertainty that exists between different models in terms of how much cooling can be achieved with a certain amount of injections. Shown here on the left, some models show very low cooling efficiency of less than half a degree for 10 teragram SO2 injections per year, while others go over 1 degree of cooling. And so if we relate this also to a study by Weisenstein et al. 2021, we see that the aerosol burden also differs substantially for the same amount of injections. And on the left of the right figure, you see SO2 injection of 5 teragrams of 3 different models. The red one is the CSM model showing much larger burden than, for instance, the ECHA model in green, for the same injections. And that also correlates to the cooling efficiency. More aerosol result in more efficient cooling. But of course, aerosol burden isn't all. And the question is, why do these models differ? And that's why we wanted to revisit this study, figuring out why, for instance, is the CSM model so much higher. So we're using 2 different microphysical schemes in the same modeling framework to repeat the study. And of course, the study has implications because it may matter definitely for various things like economical and uncertainties as well as impacts. Next slide. Seb already alluded to the different aerosol microphysics, and here I just want to point out that Weisenstein et al. Also looked at different materials to inject SO2 with this H2SO4. There is some differences in the injection material, how aerosol microphysics represent the burden, and we'll go into this as well in this study. Next slide. As I said, we use the CSM model. We use the model aerosol model, as well as the new community aerosol radiation model for atmospheres karma. And the model is represented here in green in 3 modes representing sulfates in the stratosphere, but also other aerosols in the troposphere. And karma also represents tropospheric aerosol, mainly in a mixed group, shown here in red, and also the pure sulfate group in blue, covering different ranges of the size distribution. Next slide. So we have repeated the different experiments performing SO2 as well as H2SO4 injections over 10 years in the stratosphere. And we performed regional injections in 30 north to 30 south at 19 to 21 kilometer altitude, as shown on the right left panel, and then also point injections. And you can see that the distribution differs depending on how you inject. But it also depends on how much you inject. So next slide, please. What you can see is that the model aerosol model, shown in red on top left, is almost double as high in burden compared to the sectional aerosol model. We also see differences in regional and point injections in the shape, as well as the differences between the 2 models. And in the dashed line, you see regional or injections per teragram. We see that the efficiency of the injection is reduced in both of those models. But why do we have this difference between the model and the sectional aerosol model? And that's when we can look at the size distributions between the 2 models. So the model, MEM, has 3 modes, the icon accumulation and coarse mode, but the icon mode covers a too large range to really cover the nucleation process as well. And we see that you don't have mass in the really small bins, as you can see on the bottom right of the plots. The blue squares are the sectional aerosol model. They cover much more mass in the lower bins, in the smaller bin sizes. In addition, the model aerosol model with increasing injections, as you can see in the dashed line, in the dashed red line, describes the coarse mode at a certain size, which is smaller than when you use the sectional aerosol model. So the particles do not get quite as large, and we do not get the same amount of sedimentation. In that way, we see that MEM is likely having a much larger burden because of the differences between the mode structure and microphysics. The next slide. So looking also at H2SO4, the curves have a similar shape as with SO2, but one thing that is very interesting is when we use the modal aerosol model, with increasing injection, we get actually a higher efficiency. So the burden per teragram increases in the modal model, while in karma, the burden per teragram decreases when we have 25 teragrams injections versus 5 teragram. And that is when you look again at the size distribution on the right, more aerosol mass will go into the largest bins in the sectional aerosol model. You can see the blue dashed lines versus the solid lines. While in the modal model, we see something a little bit more funny, that the accumulation mode is increasing, but there is a coarse mode that is really more at smaller aerosol sizes than the karma model. And that is actually because the modal aerosol model has been tuned for background aerosol conditions, but it hasn't been tuned for large injections. So a lot of work needs to be done to actually evaluate or to improve this part of the model. Next slide. So what is the implication for radiative efficiency? On the left, you see the net top of the atmosphere radiative forcing per 5 teragram injection. And this is in watts per square meter. On the left of the left panel, there's SO2 injections. On the right is H2SO4. And what we can see is also, okay, there's also a regional injection in squares and point injection in crosses. So SO2 injections as well as H2SO4 injections reduce efficiency with increasing injection amount. And despite what we have seen earlier for H2SO4, this is also the case in the model. So not only the burden matters for radiative efficiency, but also the effective radius and the sizes. The other thing we see is that, again, MAM has a much higher efficiency than karma in both cases, and H2SO4 is in general more efficient than SO2. That is already, it has been already shown in the study by Weisenstein. When we translate this to the required injections per watts per square meter, you do really see the large differences between the aerosol models. We do have a uncertainty or a difference between the karma blue points and the red points, especially for SO2, 25 teragrams of more than a factor of 2.5. There's also some, but a little less uncertainty in H2SO4 injections. Also, we see significant differences in point versus regional injections. So again, with MAM4, it seems like larger aerosol burden, but also larger effective radius causes in general to a larger efficiency. And considering that most of the models like GLENS and ARISE use this model, there may be some uncertainties in our results for the large ensembles. Next slide. And so what's the implication for ozone? Well, what you can compare here, this is actually color and ozone change per watts per square meter radiative forcing in percent. And if you compare the top panel to the bottom panel, for example, the top right to the bottom right, there isn't that much of a difference if you actually do SO2 versus H2SO4 injection, like the blue lines are very similar for karma. Well, actually, there's some difference in the model, but if you look at the left side, then the model differs more when we have regional injections. In summary, that means we may not actually benefit that much whether we use H2SO4 or SO2 for certain impacts, for example, ozone. And I also looked at the heating in the stratosphere, which has the same kind of uncertainty. And the next slide is then my conclusions. Please do the next slide. Yeah, so differences in aerosol microphysics can be responsible for the large differences in the models. We do see that the structure of the model can be improved, and we did find out what we probably can do to do this and explore this. And however, current modeling ensembles and other things like GLENS, ARISE, GeoMIP use the model. So we need to be careful in interpreting these results. And so there's a lot of more work also to look at different material as well as injection strategies. And so with this, I want to thank you all for listening. Thank you.
Thank you, Simone. Also perfectly on time. You would see that there's at least one question in the chat, and probably you want to answer, and it just came in the Q&A from Sean. Okay, but we can move on to the next speaker. It's Christian von Savigny.
Yes, I hope you can hear me okay.
Yeah, we can hear you perfectly.
Okay,
Thank you.
great. Thank you very much. Yeah, I want to tell you a little bit about the importance of the particle size distribution, or the PSD, of aerosols in the stratosphere. Within the World Impact project, we've been thinking a lot about how to measure and how to simulate the particle size distribution, and also how to do comparisons. And I wanted to inform you about, or tell you about, some of the aspects that we found important. Next slide, please. First of all, the first aspect is that there are some problems with measurements of the particle size distribution from remote sensing measurements. And I'm not talking about in situ OPC measurements. The OPC measurements are not affected by that. One of the problems is that we all use, or many people use, the spectral dependence, or the angstrom exponent, to estimate the particle size. But the angstrom exponent is not always a very precise measure of the aerosol size. And in this figure, you can see 3 different particle size distributions, apparently quite different, but they all have the same angstrom exponent for a certain wavelength pair, 750, 1530 nanometers. So this is one problem. Next slide, please. Another problem is that it's now a little more complicated. The different observation techniques are sensitive to different parts of the particle size distribution. And I'm trying to guide you through the figure slowly. The black line shows a bimodal particle size distribution with a main mode at 80 nanometers. And then there's a very small second mode at 400 nanometers, which is barely visible. In the so-called coarse mode fractions, the ratio of the number density is 10 to the minus 2. The blue line and the red line are the black PSD multiplied with the extinction cross-section, and also in blue with the differential scattering cross-section for LiDAR measurements. So the blue line roughly indicates the sensitivity of LiDAR measurements to the particle size distribution. The red line roughly indicates the sensitivity of occultation measurements to the particle size distribution. You can clearly see these sensitivity functions, they peak at different radii. And if you now perform a retrieval and assume a monomodal distribution, the occultation instrument will overestimate the particle size compared to the LiDAR. That's sort of one key message, and that's something that has to be considered when comparing different data sets, and also when comparing measurements to models. Next slide, please. This is kind of illustrated here. We only look at the left panel. You can see the retrieved radii in red for the LiDAR measurement, in blue for the occultation measurement for different values of this coarse mode fraction. So it's again a bimodal distribution. And for small coarse mode fractions, they both agree. But if we go to coarse mode fractions of 10 to the minus 2, 10 to the minus 3, there's a difference of a factor of 2 to 3. And we know from the OPC measurements by Terry Deschler that even under background conditions, we may have coarse mode fractions of 10 to the minus 2, 10 to the minus 3. And so there's clearly a problem when we compare particle size measurements from different techniques, and this needs to be considered. Even worse, and that's the bullet point at the bottom, is the comparison or the retrieval of number densities. The number densities retrieved from these sort of synthetic LiDAR and occultation retrievals, they differ by up to a factor of 50, so there's clearly a big problem. And that's also a general finding that the number densities from remote sensing measurements are not really well constrained. That's something to keep in mind. Next slide, please. The next slides deal with the question how to compare observed and modeled PSDs. And in the plot, you can see a 4-modal particle size distribution provided by Ulrike Niemeyer. So this is Eckham-Ham simulations, where we have these 4 modes covering a fairly wide range in particle sizes and also a huge range in number density. And the question is, how do we compare this to the measurements? And the measurement will typically only be able to see the largest particles. And I have to apologize, when I prepared the slides, I was too optimistic, so I essentially have to skip the next slide. Next, please. And next. I have to summarize this briefly. You can look it up in the slides. What we are proposing is that a better way to compare particle sizes as compared to the effective radius is to use the simulated particle size distribution and then simulate what a satellite measurement, satellite instrument would see, and then compare sort of this forward simulated satellite measurement with the actual satellite measurement. And the black line shown here is such a forward modeled and then retrieved particle size distribution. This is certainly not perfect, but it's more like an apples to apples comparison as the comparisons done in many other studies. And I'm happy to discuss this offline. Next slide, please. The last aspect is something that we started working on recently, and that's the impact of the PSD on sky color alterations caused by SAI, or also by volcanic eruptions. And we've been using SAI runs provided by Ulrike with Eckermann for different amounts of sulfur, then use the steady state. And we then use the model output PSD and use a radiative transfer model, which is Kiatran, to simulate the radiation field. From that, we can calculate the X and Y chromaticity values and also convert this to RGB and then depict the radiation field, as you can see at the bottom. So that's essentially the entire upper half sphere. SAA is the azimuth angle. This is for a specific sort of zenith angle. One important point is that the simulations only consider scattered sunlight, not directly transmitted sunlight. And I also have to point out that the colors are not necessarily realistic. But what you can see, and that's the typical output, you can see the Bishop's rings that nicely come out of the simulations here. Next slide. And we've done this for many different cases. In the left column, you can see simulations without any aerosols. There's no aerosols at all. And then the following columns correspond to different amounts of SAI injections. And you can see that there's clear differences. Unfortunately, I don't have much time to explain this, but I want to make some, somebody's posting that the slides are not visible. Can you go to the next slide, please? I want to mention a few important things on the following slides, because the Bishop's rings depend...
Christian, I'm sorry, you have 1 minute left.
Okay, thank you. The Bishop's rings depend on the PSD and of course also on the AOD. And one interesting aspect is that the radius of the Bishop's rings depends mainly on the particle size of the aerosols. In the top panel, the radius in the lower stratosphere is about 370 nanometers. In the middle panel, there's 520 nanometers. So some people cannot see the slides. I'm sorry, I can see them. In the bottom panel, we have the largest particles, and you can see, I hope you can see that the sort of the width or the radius of the Bishop's rings, it decreases as you go from the top to the bottom panel because the particles become bigger. So that would be an effect. Another interesting effect is that if you look at the bottom panel and the center of the Bishop's ring, the color is greenish. You cannot really see it well here, but if you look at the X and Y coordinates, it's fairly obvious. And that's because the particles are fairly large. If the particle size is 600-700 nanometers, then the scattering is anomalous, and then the color may become greenish. That's also a potential consequence of really massive SAI. Next slide.
Christian, your time's up, so okay, but thank you.
Okay, thank you.
Okay, thank you again. We move on to the next speaker. So now we have Ilaria Quaglia.
Hello.
Ilaria?
Yes.
Yeah.
Can you hear me?
We can hear you well.
Oh, okay. So I will be more general on model intermodal spread. So Simone shows the reason why we have these spreads among models. I want to show more in general what we can learn from model intercomparison projects. Next slide. So in general, to assess how well interactive climate models simulate sulfur dioxide emissions for stratospheric aerosol injection, we look at their natural analogs, so specifically volcanic eruptions. And we usually use large eruption like the Mount Pinatubo in 1991 as a common benchmark, because it released an amount of SO2 more than 10 teragrams of SO2, so a comparable amount with that used in SAI strategies. But these large eruptions are infrequent, and often observational data available are limited. So it's challenging to have a robust quantitative model validation. But still, small eruption like the Onga in 2022, which injected between 0.5 and 1 teragram of SO2, is also and valuable for our comparisons, because even if it doesn't have the same scale of climate impact, this still helps to understand aerosol microphysics and radiative forcing, but under a more moderate injection scenarios. Next slide. And I wanted to show you some results from model intercomparison projects. One about the Pinatubo eruption within the ISOMIP project. I'm not gonna go into details. I just want to highlight that we had several models and different injection strategies to reproduce the Pinatubo eruption, and our main focus was to investigate the intermodal discrepancies and across these different experiments. And we found challenging to have a clear and general picture of how the model were behaving for different experiments and for different variables. In general, we found that the reason of disagreement, even when considering the optimized initial parameters to reproduce the observations, these differences were depend on how the models handle the transport and the microphysical processes. And we went more in depth, next slide, evaluating the microphysics-driven intermodal spread using the model WACAM6 with two different sectional scheme, the modal MAM and the sectional karma. As Simone anticipated, MAM results having producing larger sulfate burden with the same injection settings with respect to karma. But karma results to be more efficient in extinguishing the radiation. And we can see that looking at this stratospheric AOD to burden ratio, which is generally higher in karma than MAM. And the other interesting point is that in karma is highly variable, and it decreases for large eruptions, while this efficiency increases for small eruption, which highlight the importance of including both small and large eruptions when in model intercomparison projects, because of their different microphysical response. Next slide. For small to moderate eruption, we have a model intercomparison project on the Onga eruption in 2022. The main point of that research was to quantify the radiative forcing of the eruption, but we can learn something more when we look at these three different experiments that were performed under these three different experiments that include the co-injection of SO2 and water vapor, the injection of SO2 only, and the injection of water vapor only. Generally, we found an agreement across models in the spatial pattern of the radiative forcing being stronger in the southern hemisphere, and finding that the main agent was SO2 and not water vapor. However, when we compare the two experiments in panel A and panel B, we found that in panel B, we have a more consistent response when we only inject SO2, while when we when we introduce water vapor too, the spread among models become larger. And these highlight the importance also of including in model intercomparison projects other processes like the co-injection of water vapor in this case, or for example, what could be the co-injection of ash for the Pinatubo eruption. Next slide. Going back to how we can evaluate how well model performs, we need a clear metrics to compare simulations against observations. For my Pinatubo study in the framework of ISAMIP, I was trying to quantify this in terms of correlation and root mean square error, and represent that through Taylor diagrams. In this case, I'm showing it only for the stratospheric KOD. And you can see that the figure is still complex, and it's only for one variable. So we want to develop a more integrated matrix that can combine several variables into a single framework to better capture the overall model skills. Next slide.
Ilaria, you have 3 minutes left. So
okay, yes, I'm almost done. I don't really need the other slides. So we propose to use the weighted root mean square error, which evaluate the model performance across space and over time. And it also takes into account the measurement uncertainties. Next slide. So we can in general play around, and I would just focus on the first figure, the heat map, which gives us a clear and general picture how the model performs. This can be read vertically and to understand the strength and the weaknesses of a specific model across variables, or horizontally to assess how consistently different models simulate the same variable. Next slide. And we can play with the observational uncertainties to evaluate if the bias in reproducing the observation depends on the model itself or on the accuracy of the observation. Next slide. Okay, so generally what we learn from model intercomparison projects is that we need to establish a robust matrix to assess model performance in capturing stratospheric perturbation across time and space. We need to conduct intermodal comparison for both small and large injection to evaluate the microphysical responses. And we need to incorporate additional processes like co-injection of other compounds like water vapor and ash. And also, I want to emphasize the need to have more accurate observations to enhance model evaluation and validation. Thank you.
okay, wonderful. Thank you, Ilaria. We have now Johan Freeberg. Johan, are you with us?
I hope so. I hope so.
Yeah, you are.
I'll see. Good to hear you. All right. So yeah. So everyone can hear me, right?
Yes, we can hear you well.
Yeah. Good. Okay. So I will go into the topic of experimental data now, and this started out, basically a decade ago when I started to become interested in climate modeling, and I realized that there was no data sets with sub-kilometer vertical resolution in them. So that's when it started. Next slide, please. So these are the people that contribute to this in different ways. Christine is now my postdoc, and then I have 2 PhD students here in the middle, and then it's my modeler, Moa Spotter. Next slide. Okay, so yeah, so I was working with Calypso data, and I got really used to having high vertical resolution on everything, working with 30 to 60 to 180 meters resolution or so in the vertical. And I realized that most of these SO2 sensors didn't have very high vertical resolution, or if they had any at all, it was, some of them didn't have any at all. I realized that a lot of the simulations were based on assumptions on the vertical profiles. And I figured that I could probably contribute by combining my skills in calliope with combining it with satellite data and try to make a 3D data set out of it. Next slide, please. So what my PhD student did, one of them, he combined horizontal information of SO2 data from AIRS, so a regular satellite data set with very nice and good horizontal resolution. And we assumed that the particles and the SO2 were collocated and took the vertical information from the Calypso LiDAR. And by combining these two, we could get the vertical distribution of different parts of these SO2 layers. And to add, to increase the amount of collocated data, we added FlexPart into the picture here. I'm not going to go into any kind of details here, but was simply to get a little bit more data. But we ended up getting vertical distributions of different parts of the SO2 layers. And a benefit of this methodology is that you can use more or less any SO2 data set, I think, if you have LiDAR data available from space. Next slide, please. Okay, so this is how the results from that look like. If we started out here with the AIRS data, the SO2 data, without any real vertical information. And then by combining this with Calypso data and dispersion modeling, we could retrieve quite detailed vertical distributions. And I'm not sure if it's shown here, but it has vertical resolution of 1 Kelvin in the potential temperature, roughly 60 meters in geometric altitude, and then I think around 1 millibar or so in the 2 millibars in the pressure. Okay. Okay, next slide, please. So we started to think about how, it was basically time to get this into a model. I had a second PhD student running this in the model. We started to compare just how these vertical resolutions or the vertical profiles looked, and they looked quite different from the default dataset and model and what we had produced. And this is generally the case also when we compared with former experimental data sets. We had the SO2 at a little bit higher altitude. But anyhow, this actually had made quite a huge difference in the final results when we ran the simulations. So we will see that on the next slide. When we ran simulations without data set, we get quite high stratospheric aerosol optical depth. And the aerosol remained in the stratosphere for quite long since it was so deep stratospheric injections. And when we compare this with the default data set, the black one here, you see that the perturbation here is roughly a factor of 2 or so in difference. So 100% higher stratospheric aerosol optical depth when you run this with our high vertical resolution SO2 compared with the default data set. Sorry that I don't have any much details here, but if we just go into looking at the clear sky volcanic forcing, it also made a huge difference since the aerosol did not survive very long in the stratosphere. In the default case, it was roughly half a year perturbation to the radiative balance. But when we injected this a little bit higher from our experimental data or our satellite observations, it seemed to last a little bit longer here. So it effectively, if we take the next slide, we'll see. So the effective radiative forcing became twice as high in a 1-year perspective. So apparently quite much more cooling them. Okay, next slide. So the idea now we have just produced this for one volcanic eruption. I may have forgotten to say it was the Sarychev eruptions in 2009. So the second one in this time scale here in the picture. We are currently trying to produce this for all major eruptions in the Calliope era. And then hopefully we'll bring it into the future also with the Athlid era and combine it with that LiDAR data set. And we hope that this could bring, that we could produce a high vertical resolution data set for each and every of these major eruptions. Okay, next slide, please.
Johan, you have 1 minute left. Oh,
yeah. Okay.
Great.
So basically, what is now quite rapidly in a couple of different studies, but we managed to produce some vertical profiles by combining SO2 data with high vertical resolution from data from Calypso. And I think the benefit with this methodology is that you can use it for any satellite-borne SO2 sensor. And our near-term goals here is to use it for each and every major eruption in the Calliope era and also in the Athlid era, no matter how long that may be, hopefully a decade or more. Regarding the simulations that we ran, this was just a test in WACM that we did very rapidly, but we could see that it produced quite high AODs. The AODs that it produced were quite similar to observations of aerosol optical depth from Calypso during the first year. So we're quite confident that this is good stuff. Or maybe this shows that the model itself is really good. I don't know. But it made a huge difference in the 1 year ERF for the cooling. Okay, thanks for listening to this quite rapid talk.
Thank you, Johan. Okay, we can move on to the next speaker. I apologize in advance for not pronouncing correctly, but is Ayase Koyun?
Yes, it's Aisha, no worries.
Aisha, sorry. Apologies. Floor is yours.
Thank you so much. Also thank you for the organizers for putting this workshop together and the panelists and the speakers. Today I'm going to talk about the work on optical properties and ice nucleation activity of alternative SAI materials. Next slide, please. Okay, so the way we look at alternative SAI materials is we have the bulk material of the aerosol particle and the surface, where the bulk material is mainly responsible for radiative forcing, diffuse versus direct radiation, which has implications on the stratospheric heating. And the surface, which is the outermost layer, which is responsible for heterogeneous chemistry, ice nucleation activity, and coagulation properties. We'll see later that how some particles tend to agglomerate and then later deagglomerate when they're in a solvent. So the questions I'm going to address today is how do properties of commercial particles compare to ideal ones, and also about the ice nucleation activity. I'm not looking at HCl and UV today, but also not important, but questions that we are generally not looking at is cost of ideal particles and how to disperse or how to spray those aerosol particles, and also the sinks impacts in the troposphere and surface. Our main motivation is definitely to look at ideal particles and also look at Earth abundant particles to not introduce new materials into the troposphere. Next slide, please. So here's the particles that we investigated. We look at particles like different type of carbon or diamond particles of various particle sizes from 100 to 200 nanometers. Then alpha lumina and calcite, magnesite, zinc carbonate, and calcium magnesium carbonate, which is dolomite. These are all earth abundant materials. And yeah, Frank said, why don't you just look at the reactivity of aqueous HCl with those different calcites. And it turned out that they are very different. Magnesite, for example, has a very low reactivity with aqueous HCl, although all of these calcites show a very similar optical properties. And this is also one of the criteria how to choose an ideal SAI candidate. Next slide, please. So I also want to show that we compared commercially available particles to cut gems from the museum. So there are sometimes processes in the industry that involves processes that alter their optical or chemical properties. They introduce trace materials or defects that can show up either in infrared or the UV spectrum. So it may alter their scattering efficiency and absorption, and that's why we compare them to bulk materials from the museum. Next slide, please. So when we look at the commercially available materials, we confirm with X-ray diffraction. These are measurements that David Werber, the grad student he measured calcite and alumina. We see that the bands are overlapping. They match the literature data, but for diamond, we see that these are 4 different kind of diamonds on the right-hand side. We see that there is not a sharp peak at around 40 to 45 angle, and we see that detonation diamond has, for example, a small crystal domain size around 4.5 nanometers, and the high pressure, high temperature diamond has a larger crystal domain size. And David was able to determine the crystal domain size of the different diamond materials, and this is especially important for scattering efficiency, as internal reflections plays a role in small crystal domain sizes as well. Next slide, please. So if you look at this is an SEM image on the left-hand side and an AFM image on the right-hand side that I took of the detonation diamond, and they say it's 100 nanometer. And from both AFM and SEM, we see it appears to be larger than 100 nanometer. But if you look closer at the AFM image on the right-hand side, you actually see that those individual particles are around 100 nanometer, but they are stuck together. And you can also see how porous this material is. And our collaborators at KIT, they did some work on this. They took this detonation diamond and looked at their isonucleation activity in the AIDA chamber. Next slide, please. And now what you see here is on the x-axis is the different temperature, and the y-axis is supersaturation of ice where you see freezing. Bismuth triiodide is very well known as a good isonuclei, and diamond dust shows an even better isonucleation activity with a supersaturation of below 1.2 at different temperatures. And there is an ongoing speculation why this is a very good isonuclei. And yeah, we think it could be the porous nature, which makes it a great isonuclei, probably because there are more active sites where isonucleation can occur, and that increases the probability, but it is still a speculation. Next slide, please. So we also took these materials, mixed it with a solvent. I think it was isopropanol, but it doesn't really matter, and put it in an ultrasonicator. And that's the treatment process for dynamic light scattering. And during that treatment process, it actually de-agglomerated. And we see that the particle size in this spectra is around 100 nanometer, which matches the vendor's data sheet. Although we see in AFM, it clearly was not 100 nanometer. It shows as agglomerated, but if you treat it in an ultrasonicator, it de-agglomerates again. And next slide, please. So next thing is we did FTIR, and this can be a diamond or a germanium crystal, depending on what material you want to measure. You press your bulk material on top of the window and press it, and then you measure the infrared spectra. Next slide, please. Now, let's look at the properties of calcite. What you see here is that calcite and aluminum match the literature data, and what we care here is the atmospheric window that is between 800 and 1400 wave numbers, and ideally they show no absorption in these regions. And this is not a quantitative spectrum, these are relative values. Next slide, please. So these are the infrared spectra of calcite compared to smithsonite, magnesite, and dolomite from the museum. They are very similar, have very similar optical properties, and we know that their chemical reactivity with HCl is quite different. Next slide, please. And yes, here is the infrared spectra of the different types of diamond. The window that we care about is 800 to 1400. And you see that some types of diamond show absorption, and the type 2A, for example, doesn't show any absorption. And we are looking for these features in the diamonds that we purchase. Next slide, please. So we compared it to the diamond from the vendors, and we see that there are some kind of absorption between 800 and 1400, and those come from nitrogen and boron defects. And we also see an sp2 absorption, which is a graphitic absorption around 1500, and sometimes it appears around 1600, depending on the hybridization. Next slide, please.
You
So
have
what I
1
showed
minute
you
left.
up to now, okay. Up to now, I showed you infrared spectra of bulk material or pressed particles. And if you want to do infrared spectra of single particles, you can do scanning near field optical microscopy, where you can measure reflectivity, absorption, and topography at the same time. And so this is a way to get complex refractive index of single particles. And next slide, and this can be my last slide, I can show that on the left-hand side, you see the topography, the optical amplitude when compared to a silicon substrate. It shows a very close reflectivity to silicon, and then the absorptivity, which is lower than the silicon. So thank you so much.
Thank you. Thank you for your presentation.
Mhm.
Okay, we can move on to the last speaker for this session, and then we'll have a brief session discussion. So now we have Kwesi Kwagren.
Yeah, hi,
Kwesi,
thank you.
are you with us?
Yeah, I'm here.
Hi.
Thank you, I'm with you. The slides keeps on moving, not mine yet. Hi, thanks everyone for being here today. Today I would be presenting on sort of exploring variable resolution CSM framework for improved simulation of regional climate over Africa. I would like to acknowledge contribution from Simone Tilmes and Isla Simpson, and I'll proceed. Next slide, please. Yeah, so our current geoengineering models are typically of a resolution of 100 kilometers per grid, and that limits the kind of details that we want to understand when it comes to impacts. And of course, it would fall short of capturing the regional dynamics and localized impact of SAI. And by refining these models, we hope that we can better assess the potential impact of SAI. Next slide, please. So the method is typically using CSM2, Wacom 6 SAI and SAI runs for both historical and future periods. And then we used sort of SSTs that were consistent with the SSP 585 scenarios. And we used a pre-built variable resolution mesh over Africa, where we have any 30 grid outside Africa and then a 0.25 degree within Africa. And of course, the physics is based on Wacom 6. And then we use our prescribed SSTs from the Wacom 6 SSP 585 runs. And of course, the period that we use for historical is 2010 to 2030. And then for future target period, we use 2080 to 2099. Next slide, please. So I'll skip this because we know that our models sort of over the years has improved in the kind of responses that we're able to measure from the models, especially with high resolution models. Next slide, please. So this is just a baseline evaluation of our models. One, on the left, you have the Era 5 annual mean surface temperature. So the segment that you see on panel A is literally the IPCC Africa regions, ARSS Africa regions, and we wanted to see how variable resolution impacts these regions. And for this, we see that on the left, panel C, The variable resolution CSM, of course, has improved the responses that we get from temperature responses over the region. Next slide, please. So we intended to look at the seasonal distribution as well. And we see that variable resolution CSM does reduce the mean seasonal bias relative to error 5 when you look at the third column on the right. We see improved correlation as against reduced mean absolute errors, which was good to see. Can we go on to the next slide, please? And for precipitation, we found really interesting responses because on the left panel A, you see the chirps that we use as an evaluation. And then on the right, far right, you see the variable resolution CSM chirps. We could see very good responses over orographic and coastal regions. And that helps with the variability fidelity of the model and the kind of responses we are getting. And clearly, although we lose the correlation and then some absolute errors, we are able to get this response from these orographic regions that were not necessarily the responses that we got from the NE30. Next slide, please. Next slide, please. Yeah, for seasonal distribution, that's okay. So here is the crux of the issue. We wanted to see, does resolution matter in where rain falls under SAI and non-SAI under these two different resolutions? Clearly, we can see I would focus on panel C, D, and HI. And clearly, we can see that SAI, the variable resolution, does change the response to SAI, in particular, the distribution of the precipitation. And clearly, we can see, of course, the biases that we see are very different, especially for West Africa, for instance. We see some dry biases that are in panel H that are not present necessarily in panel C. And similarly, that response is a little bit magnified in our variable resolution when we take no SAI with SAI. And then that response is also seen, a different response is seen for the NE30 grid. So that means that resolution changes where rain falls, and SAI sort of redistributes the moisture globally. And moisture for future changes on the last panel were not really robust. Next slide, please. So we wanted to understand how does this impact extremes. So this is just probability distribution function of precipitation. Here we are using iMerge to do the evaluation of these models. And the red is variable resolution CSM for historical in solid red and for future in broken red. And then similarly for black, you have NE30, and then for dashes, broken dashes for NE30 future. Clearly, we can see that there is an improvement in the response of SAI and precipitation, especially for some regions, and other regions we do tend to deviate. And this is for JJA season. And for instance, if you take somewhere like the Sahara, which is the B, you can see that the variable resolution CSM does improve the response up until a little bit higher, like above 200 millimeter per day rainfall rate. And that is something that we did not really see in the NE30 responses. Next slide, please.
Kwesi, you have 1 minute left.
Absolutely. And this is a similar response to the DGF season, where the models deviate in some regions, whereas other regions we have very good responses. Next slide, please. So in summary, we have reduced biases versus the error 5 and chirps in the variable resolution CSM model. And we also have better coastal and orographic rainfall placement, which improves the variability. And then also we have smaller errors for the extremes as compared to the NE30. And then there is a clear separation between SAI and then no SAI. And then resolution has influence on the regional impact, especially for rainfall. So we hope that this sort of model runs would help provide policy relevant signals for water and heat risk in Africa. Thank you.
Thank you. Thank you, Kwesi. Your presentation brings to an end this first session, and now we have some time for discussion. If anybody has any questions that they haven't had time to ask in the Q&A or in the chat, are welcome to, or if anybody who has been chatting in the chat wants to bring their question forward. There was a very interesting Q&A between Jean-Paul and Johan. I don't know if you want to expand on that.
Let's see. Sure. I will need to check the question again here. But it's regarding if we can be certain there is no bias in the vertical separation of SO2 and aerosol, I guess. And that is indeed difficult. It's what we did is that we checked whether we had any separation of aerosol sizes by looking at the color ratios of the Calypso. We also checked that we had limited impact of ash particles to rule out that we had large ash particles settling and putting the SO2 at, the aerosol at a little bit lower altitudes than the SO2. But it's difficult to know. But when we compare the AODs 1-2 months after the eruption, it is the vertical profile, so that is almost identical to the SO2 vertical profiles that we produced a few days after the eruption. So we are quite certain that the methodology worked well for the Stratospheric eruption. It's
Thank you, Johan. Yeah.
Thank you. Yes. Sean, I don't know if you want to discuss what you were asking about in the Q&A as well. Asking about H2SO4 versus SO2. Maybe this is a discussion that other people want to hear about. If you're still up. Although maybe he can't be unmuted. Simone, do you want to give a summary of what you were discussing with?
Oh, yeah, of course. The question really came to why would we see a higher efficiency for H2SO4 injections in the model? But we didn't see that really in the Karma model. And we do expect that if we inject H2SO4, we keep the sizes smaller. That's the whole idea of using accumulation mode SO4, because we don't have the condensation that we have with SO2 and also the nucleation. But in the model, it is interesting that we actually get a larger efficiency, while in the sectional model we don't. And the reason for that is that we see that the sizes don't grow as large in our model. And I think it is because our model, our coarse mode, has a small sigma that wasn't tuned for the large injections. And so we actually keep aerosols smaller, so we accumulate more mass. And what comes on top of it is when we have more mass built up with more injections, we get more heating. And that also causes the particle to get lofted up more with the rhodopsin circulation, and therefore removed less. So we think that is a process that is likely an artifact of our model, aerosol model. But it will be interesting to further look into other models as well. Is that helping?
Yeah, thank you, Simone.
So
yeah, and I see another question from Sean.
Daniel, So Daniel, my question is, fundamentally, is it an artifact of the model, or is there something physical? Because everything else being equal on a per mass basis, so is it really something that's just physically always going to happen? Or so very low injection rates, very high dispersal, different nozzles and things like that could you ever design it so that actually it could be more efficient to inject SO2? That's out with the modeling assumptions at the moment.
Yeah, and just should I answer or sorry?
Please, Simone. Yeah.
Oh, okay. I mean, you have to keep in mind also that we're using a 100-kilometer grid box here. For SO2, if you want to really design and explore this, we do need to go to larger resolution and plume sizes discussion that we had yesterday. For SO2, that may be less relevant because SO2 forms sulfate much slower. So putting something in a bigger model box may be in some regard okay. But if you do an aerosol particle, it really depends on how many particles, the number of what you inject. So what we are seeing here is really a bit idealized. right? And so, yeah, I
Mhm.
think that's the question. Can we actually produce something that is more efficient? But I think the first step is to understand if our models do the right thing. And if we already doubt that what our model is doing, then maybe using more comprehensive models will be the first step.
Yeah. And I can also point out, Seb, who's here, had some work on sort of the pluming grid. So nesting a plume model inside a grid, that is an interesting approach. And also the fact that even some original observation by Dave Fay, actually back in the 80s about rocket plumes, indeed showed that when he said that the plume remained very compact after rocket launches, they still see a diffusion over 100-kilometer horizontal scale after a week or so. So there is diffusion going on. And so, but it is interesting to see the fact that we haven't done that in the climate model. So we have this assumption of uniformity to tangle with. Okay, these bring us to the mini break. You have a 3 minutes break, and then we'll continue with the second session. Thank you everybody for joining this first panel and discussion.
So hopefully people are starting to come back from stretching their legs for a few seconds. And we'll get ready to start the second session. Leo, are you there?
Yes.
Maybe. You can go ahead and start bringing up the slides. And I believe our first talk today in this session, which is SAI simulations, strategies, and scenarios, is by Wake Smith, and the title is Bounding the Possibility Space for SAI Deployment Scenarios. Wake, are you there?
I am. Can you hear me?
We can indeed. Go ahead and start.
Great. So SAI had previously been represented as a sort of socio-technical imaginary, where it wasn't clear how we would do this and it wasn't clear what the boundaries are. But I'm going to try to focus on some of the physical and technical boundaries that bound the possibility space for deployment scenarios. Next slide, please. So this is the SAI cartoon that was produced several years ago, commonly shown, comparing volcanic eruptions to SAI. For this discussion, the importance of this slide is the horizontal line that runs through the middle of it. For SAI to be effective, we've got to deploy above the tropopause, which is what that line represents, and well into the stratosphere. Next slide, please. Why so high? Injections in the troposphere last for days or weeks, whereas injections in the stratosphere last on the order of a year or more. So high injections achieve a roughly 100 times radiative benefit that low injections would achieve. The diagram on the right shows the location of the tropopause, the altitude of the tropopause by latitude. And what we see is that the tropopause is much higher in the tropics than it is at either of the poles. So if we are going to inject in the tropics, which is what would be necessary to create a global veil, we would need to inject at roughly 20 kilometers or 66,000 feet, which is much too high for most aircraft. Next slide, please. So passenger jets in the upper left-hand corner can't get there, nor can military tankers in the upper right. Fighter jets could get there for a few seconds in a ballistic climb, but that doesn't work for deployment. The Global Hawk drone in the bottom right-hand corner can nearly get to this altitude, but with almost no payload. Next slide, please. Other lofting platforms such as balloons, rockets, cannons, tethered hoses held up by balloons don't work for other reasons. Next platform, please. Next slide, rather. But capable planes could be developed, and with a team of Boeing engineers, we had developed a preliminary design for a plane that could serve this purpose and haul high payloads to high altitudes. But a key constraint to note here is that the developmental time span for such a plane is roughly a decade, which makes this inconsistent with the climate emergency framing that is so often portrayed in respect of SAI. Next slide, please. But if we did take the time to develop the right plane and deploy in the tropics, then the Brewer-Dobson circulation, which is what's represented in the figure here, would take our material that's deployed again in the tropics above the tropopause and spread it to the entire globe, creating a roughly homogeneous global veil and shading the entire planet then. Next slide, please. But the deployed mass requirements for that sort of planetary deployment are huge. 1 million tons of SO2 per year would roughly equate, with all of the discussion that's previously been had about uncertainty here, but 1 million tons, roughly 1/10 of a degree C cooling, so 10 million tons for a degree. That's a lot of stuff. Dozens and eventually hundreds of large aircraft would be required to do that, representing thousands and in fact tens of thousands of flights per year. This makes this sort of global intervention much too large to be done secretly. After all, a large fleet of large aircraft would be easily visible to satellites. And so one thing we don't need to worry about is whether nefarious actors could covertly hack the climate. This is also too costly for non-governmental actors and is instead the domain of large states or coalitions among them. Next slide, please. SAI could be harnessed to serve several different objectives. SAI could, for instance, recool the planet, and that makes it distinct from either mitigation or adaptation, which cannot recool the planet. Carbon capture can cool the planet, but it may require decades or centuries to do that. But reversing warming, recooling the planet, is an extreme SAI choice. It implies much bigger deployed masses with concomitantly magnified risks, and societies may have by that time adapted to the warmer temperatures and may not want to turn back the temperature clock. So halting or slowing warming seems like a much more prudent objective. Perhaps, for instance, we stop warming at 2C in roughly 2050, with deployed masses growing gradually thereafter as concentrations thereafter grow. Next slide, please. In terms of where to deploy, latitudes of injection matter. Once again, a tropical set of injections would create a global veil, but longitudes don't seem to matter insofar as we currently know. The veil spins rapidly around the globe, and so conceivably one could deploy from any longitude in order to get a global effect. One thing we ought, however, to do is observe hemispheric symmetry. If we don't deploy roughly symmetrically in both hemispheres, north and south, we would disturb the tropical rain patterns that obtain in the middle of the planet, in the tropics. We also would want multiple bases in many countries in order to provide resilience against both natural and human disruptions to the SAI program. A constraint is that regional or national deployment doesn't work. The veil quickly exits any target area. Next slide, please.
2 minutes, Wake.
The exception to that regional comment is the poles. The poles are warming 3 times or more faster than the global average. Melting ice or permafrost threatens the entire planet. Many of the tipping elements that we worry about reside near the poles, the AMOC perhaps being the most worrying. High latitude injections would preferentially cool the poles, but they would have effects everywhere all the way down to the equator. But they would slow the ice melt and stabilize the AMOC to the benefit of the whole planet. Polar injections can be done at much lower altitudes with existing aircraft because, once again, the much lower tropopause height at high latitudes. So we could ramp up easier and faster and more quickly. Next slide, please. Timescales. Again, I would propose that we not consider SAI an emergency intervention. There is time required to assemble the infrastructure and likely even more time required to assemble a governance structure. It would be prudent to ramp up slowly over several decades in order to avoid an initiation shock that a binary turning on of a light switch would represent. This is not a one-time shot. We would need to do this continuously year-round. It's not short-term. It might continue for a century. And just as we would ramp up slowly, we would seek to ramp down slowly in order to avoid termination shock. Next slide. But if we needed to do this, the likelihood is very high that we could do this. Thank you.
Thank you, Wake. And now we will move on to our next present. And Wake, there is one question for you in the quick Q&A. Our next presentation is by Pete Irvine, and it's on peak shaving with solar radiation modification to shorten global temperature overshoot. Go ahead.
Morning. Thanks for having me. Yeah, I'm presenting some work here by Linus Baselius, Alistair Duffy, and myself. Peak shaving with SRM would shorten global temperature overshoot. Next slide, please. So, setting the scene. If we do not cut emissions, temperature will evolve something like this. You can see global mean temperature rising over time out into the future. So if we don't cut emissions, the planet keeps warming. Next slide. If we eliminate emissions, we get to net zero. Temperatures will stop rising, but they won't fall very quickly. You can see the x-axis here runs out to 2400, and even several centuries after eliminating emissions, temperatures aren't that much lower. Next slide. And that's why people are considering removing carbon at large scale. This is a fairly large scale deployment of CDR that fairly rapidly lowers temperatures, but still in this fairly semi-pessimistic scenario of future emissions, we would overshoot 1.5 Celsius for several centuries. So solar geoengineering could come into this picture, potentially, as we've been discussing, and potentially offset, peak shave that. And one would think you would need it for as long as temperatures overshoot your target. So if we want to keep temperatures at 1.5 Celsius, we need it for that whole time shown here. Next slide. However, as this illustrative plot shows, there's a little deviation we've discovered here at the end. You need SRM for less long than you might think. Next slide. This study is going to explain why and how we found that. So we generated a scenario based on the SSP2 4.5 scenario. So it's a semi-pessimistic scenario, but we edited it so that after 2100, they kept cutting emissions and then they go net negative. So we have a slightly altered end that goes to fairly large CDR scenario, minus 10 gigatons CO2 a year. So you get this kind of classic temperature overshoot. Here we simulated that in the FAIR climate model, a very simple climate model. And then we generated a whole host of ensemble members tuned to reproduce the behavior of the broader climate models in the CMIP6 ensemble. Next slide. And we implemented SRM in a simple way, turning down the sun in the model, and used a feedback algorithm, hence the wiggles here, to keep temperatures, in this case, at 2 Celsius. And we looked to see when would overshoot end in this scenario, and we found it ended earlier. Next slide. Why is that? I initially thought it would be the carbon cycle. A warmer world weakens the carbon cycle, weakens the uptake of CO2 on land in particular. Melting permafrost, degrading soils add CO2 to the atmosphere. I thought that would lead to a significant amount, which would then delay the recovery. However, the two lines here, the red and the blue, show the difference it makes. Small. And the green sort of is a zoom in on that, showing that it amounts to 2 to 3 parts per million averaged over our ensemble. That's about a couple of years on that trajectory. We're looking for 40, 50 years of difference, and we've only got 1 or 2 from the carbon cycle. So what's responsible? Next slide. The oceans. So here you show global mean temperature, the surface temperature in the solid line, and then deeper layers of the ocean in dashed and dotted. And you can see that in the standard overshoot scenario, the ocean temperatures of these deeper layers lags behind the surface temperature. So the planet warms, but it's sort of slowed down by the heat that's going into the ocean. And then as the planet cools, it's again slowed down by the heat that's in the ocean, kind of pushing back, resisting that fall in temperatures. Next slide. So if you add SRM and you cool the surface, you also cool the ocean. And so there's less heat in the ocean to resist the drop in temperatures that will come as you clean up the CO2 from the atmosphere, meaning you can end your deployment of SRM much earlier because the ocean wasn't made nearly as hot as it would have been in a scenario without SRM. Next slide. So we did this across a whole ensemble of models with varying carbon cycles and climate sensitivities, etc. And we found that, shown in the left here, all these little dots, the longer the overshoot, the larger the reduction, or the larger the reduction in the overshoot duration. So big overshoots tended towards a 20% reduction in the duration when you deployed SRM, whereas the shorter ones, we get more like a 5 or 10% reduction. Next slide. So yeah, this is a lovely paper in Oxford Open Climate Change. Do check it out. I think it's quite reasonable that we can expect centuries-long overshoot with current policies, which are not looking so great and could lead to 2.5, 3 Celsius of warming. If we go ahead and do large-scale CDR, we're in it for centuries. Deploying SRM on top would shorten overshoot by circa 20% in this first study. I'm sure others will do more work to refine that, but it's a substantial reduction in overshoot. So peak shaving with SRM leads to overshoot shortening. Thank you.
Thank you very much. Very interesting talk. And well in time even. Our next speaker is Doug McMartin, who's going to talk about managing uncertainty in SAI through learning across scales. Oh no, I got it. Patrick. Doug will be after that. Designing scenarios for exploring unilateral climate intervention. Sorry about that. Go ahead, Patrick. Okay, we can't hear you. It looks like you're unmuted. We still can't hear you.
How about now?
Now we can. Great. Go ahead.
Okay, great. Okay, so next slide, please. So in case I run out of time or you have to leave, this is what I'm going to say in my talk. Scenarios serve multiple purposes. We're going to talk about, I'm going to briefly revisit what scenarios are for at the top of this talk. Societal perception ought to be an integral component of climate change scenarios, including SAI scenarios. Physical changes in the Earth system will be observed, interpreted, judged, and acted upon in a variety of ways, and that unilateral scenarios or minilateral scenarios ought to be designed consistent with these features, including widening the scope of what is considered plausible. Next slide, please. So I wanted to start by just saying, what are scenarios for, and trying to revisit some early work that's been done thinking about what scenarios are for, particularly in the environmental and climate context. Next slide. So Raskin et al. In 2005 said, scenarios are plausible, challenging, and relevant stories about how the future might unfold, which can be told in both words and numbers. Scenarios are not forecasts, projections, or predictions. They are about envisioning future pathways and accounting for critical uncertainties. The process of building scenarios is about asking questions as well as suggesting answers and guidance for action. It is intended to widen perspectives and illuminate key issues that might otherwise be missed or dismissed. By the way, I'm not necessarily saying all of these are accurate, but there's a range of definitions of scenarios. Next slide, please. This is from Schweitzer in 2016. Scenarios are tools for analyzing plausible alternative future trajectories in a complex system in which there is considerable uncertainty of outcomes when determining future developments. Scenarios can provide scientifically defensible narratives that describe future developments based on major driving forces and their impacts. Scenarios are useful in creating a bridge between science and policy by exploring deeper implications for different decision paths. Next slide, please. And this is from Peter Schwartz. A scenario is a tool for ordering perceptions about alternative futures in which one's decisions are played out. Its purpose is to improve decision-making today, not to get an accurate prediction of the future. The test of success is not in getting the prediction right, but in proving action now. And just next slide. Schwartz has a lot of really kind of juicy quotes, so I'm pulling one more here. Rigorous models are needed that lead to different conclusions, different interpretations of history, leading to different projections. Building models thus requires both rigor and imagination, even for a 50-year time frame, though perhaps even more so for a 500-year time frame. People are remarkably capable of failing to see signals of impending change. Good scenario thinking allows one to see the signals of fundamental change when they arrive. Next slide. So just a quick sum up of that. What are scenarios for? Envisioning future pathways and accounting for critical uncertainties, widening perspectives and illuminating key issues that might otherwise be missed or dismissed, analyzing plausible alternative future trajectories, ordering perceptions, and improving decision-making today. Next slide. So with that in mind, I want to make the point that perception has to somehow be integrated into SAI scenarios in general, but unilateral scenarios especially. But how? So here, what we have is, this is a figure that's probably familiar to some of you. On the x-axis, we have time. On the y-axis, we have global temperature. And we can see this is from the ARISE SAI experiments that have been talked about already during this workshop. Marching forward in time, we can see that around 2035, SAI is deployed globally. And in the absence of SAI, the temperatures keep marching up. SSP 245, that's the same scenario that Peter mentioned in the previous talk. In 2035, we see that starting there, the ARISE SAI deployment is effective. Temperatures stay relatively stable, and they don't increase further. Next slide. When we look at this as a map, on the left-hand side, we can see these are the trends in warming over, in this case, a 20-year period. And that following SAI deployment on the right-hand map, we see that there's no trend. The planet has stopped warming in this case, more or less. Next slide. The problem is we aren't going to live in the average of, in this case, 10 different worlds. We're going to live in a single world. And so we have to come to grips with the fact that we will be experiencing the natural variability that's inside that world. And so in this case, we have a somewhat more condensed trend, 10 years of change, both on the lower left-hand and the lower right-hand side. The lower left-hand side shows the 10-year trend in temperature prior to SAI deployment. And we see a lot of heterogeneity. That's not saying that SAI, or that's not saying that climate change isn't happening. It's saying that natural variability is happening on top of climate change. We see heterogeneous temperature trends around the planet. On the right-hand side, in the 10 years following deployment, we can see similar but different temperature heterogeneity. And this is simply the fact that the 10-year trend might be dominated in some places by substantial natural variability. We have to somehow come to grips with the fact that society is going to see something that's closer to the bottom panel, rather than know that we're living in a forced climate that is experiencing long-term trends. Next slide. So a result of this is that society may incorrectly assign changes in temperature to SAI when it is in fact natural variability, or vice versa. There's the risk that there could be a perception of success or failure, but getting the reason wrong here. And so as an illustration of this, we can see in this figure that among the 10 ensemble members of the ARISE SAI ensemble, that Beijing, for example, experiences 4 different types of possible worlds before and after deployment of SAI. And these are 10-year trend lines. So the yellow is 10 years and the green is 10 years. And the take home here is that you can either be warming or cooling prior to SAI deployment, and you can be warming or cooling afterwards. And again, I want to drive home the point, this is not because climate change is different for these different scenarios. It's just the fact that natural variability is different across these scenarios. Next slide. As a result of this, substantial fractions of global society may be exposed to surprising or unanticipated conditions. This is a figure that shows that 40% of the time, or 4 out of 10 times, the areas in red experience the possibility that temperatures could go up after SAI deployment. So this is the probability of perceived failure, that people might perceive that their temperatures are not following what they would expect to happen after SAI. Next slide. So how will perception affect how society responds to changes in temperature? We can sort of speculate about how, this country or that country might react. I've taken some of that work that I just showed you and applied it using some game theory to understand unilateral interaction. Here, what we can do is maybe go back 1 slide really quick. Okay. Never mind. Forward. I'm not sure where the red line came from, but that's okay. I can incorporate it into the talk. Why not? All right. So how will perception affect how society responds to changes in temperature? What we can think about is the fact that perception is just one part. And I don't think you can see my cursor, but if we look at the bottom of this little causal loop diagram, we can see perception feedback. People will perceive the climate in one way or another, but that perception then flows into different aspects of cognition, how people form opinion, and then how that opinion is expressed via voting or just policy action if there's no voting, into changes in terms of emissions change. This is a model produced by Fran Moore and colleagues, published a few years ago, that allows us to sort of peer into, in this case, a parameterized version of how global society might interpret changes in temperature, how that is processed through people's behavior, through policy, through eventual emissions changes, and then further back to changes in temperature. We can think about this as a way for interpreting and understanding how society might detect and make sense of changes, in this case, emissions changes, but also you could use this to understand how SAI might be detected. Next slide, please. So for example, in this particular model, we can see that perception and cognition are connected to one another. So how might bounded irrationality affect policy enactment in the context of SAI deployment? Next slide. How might deepening, partisan political divides upend assumptions about political policy continuity? We're talking about commitments that are measured not in years, but measured in decades, if not centuries. And we have to somehow come to grips with the fact that our scenarios of SAI have to start grappling with really challenging ideas related to politics and policy. Next slide. So what are we missing in unilateral scenario design? But we could step back and say in most scenario design when it comes to SAI. Next slide. Ultimately, we need much more social science to better understand what's going to happen. How might this unfold? That can be based on surveys, models, etc. For example, how will society respond to SAI-induced temperature changes is it the same as how they respond to natural variability? Is it going to be the same as emissions-related temperature changes? If not, why not? We need to better understand what these reactions might be. What tools, back to Peter Schwartz's point at the top of this talk, what tools would permit us to better sense impending surprise? What are the things we need to be paying attention to, particularly on the policy, the society side, that could very consequentially steer or affect SAI deployment scenarios? Lastly, we need a deeper inventory of possible motivations for pursuing unilateral SAI, but in general for SAI across the board. But this includes things like non-technically optimal scenarios, things that might not work, things that maybe aren't intended to work, non-long-term oriented scenarios. What would it look like if somebody only has a game plan for the next 10 years? Is that scientifically optimal? Absolutely not. But that is potentially a possible motivation for an actor. And then finally, non-economically rational motivations. Again, we're living in a world where we can observe every single day non-economically rational behavior. So we have to somehow be able to fold that into the way we're conceiving of scenarios. Next slide. So I just want to briefly say thank you to these folks. This is Elizabeth Barnes, Jim Hurl, Chunrei Diao, Curtis Bell, and James Larson. They've all contributed to this work. If you have questions, please feel free to reach out. Thank you very much.
Thank you very much. And now we will have Doug McMartin talking about uncertainty in SAI through learning across scales. And there is one question to you, Patrick, in the Q&A. Go ahead, Doug.
Thank you. So I'm not going to show any quantitative results on anything. I want to make a few broad comments about uncertainty and learning across scales. And the first one, just for a fun picture here, I think that there is a tendency quite often when we think about uncertainty in SAI and, oh my gosh, our models don't agree and so forth, to envision a choice to deploy someday in the future as like jumping out of an airplane and hoping that your parachute works. Next slide, please. But that's just fundamentally the wrong analogy. I've also heard people talking about this as like equivalent to introduced species. You can't unintroduce the cane toad from Australia. You can't unjump from an airplane. But because the lifetime of aerosols in the stratosphere is of order a year, you can always revise what you're doing. Next slide, please. So I want to talk about the various scales, particularly of outdoor activity, that I think would be scientifically useful. I'm not going to talk about the governance that is appropriate at each scale directly. So right now, of course, we're doing modeling. We're looking at stratospheric observations from volcanic eruptions and so forth, and observing climate change getting worse. Next slide. The next scale of activity that would, I think, be scientifically justified is to conduct a small experiment, basically fly one airplane up to the stratosphere, release SO2 or whatever, in order to help reduce the uncertainty in aerosol microphysics. Simone pointed out the big differences, factor of 2-ish differences between models in how much you need to inject to get a given amount of cooling. In addition to that uncertainty, there's also the issue that we validate our climate models largely on observations of things like volcanic eruptions. But if you are going to fly an airplane for SAI and release sulfur dioxide, that does not look exactly the same as a volcanic eruption. And the only way that you ever actually resolve that uncertainty is by conducting that experiment. Next slide, please. I would guess that if we were to conduct that first scale of activity, there might be a number of tests that one would do of that scale. The next scale that is likely to be scientifically justifiable would be now take that airplane or a couple of airplanes, and instead of releasing something of order 10 to 100 tons, one's releasing maybe 50 kilotons. I don't know whether we want to call that an experiment or a subscale deployment. The reason that one might do that is to validate our uncertainties in aerosol transport and lifetime. Next slide, please. And really the point of going through that is to say, at the point at which one would be facing a decision to deploy in a way that's actually reducing temperature, and therefore a way that would actually be incurring any physical risks associated with uncertainties in the science, one would have already resolved or largely resolved any of the uncertainties in the stratospheric processes associated with aerosol microphysics and size distribution and transport. I actually don't know the question, and I think it would be valuable to actually quantify in our climate models exactly how much of the uncertainty in the things that we really care about, surface climate stuff, arises from those sources. Even at that point, of course, it's not a blind decision to deploy. We are currently warming the temperature at warming the planet by something of order 1/4 degree per decade. If you are in a peak shaving scenario, that means it's about 20 years before you're at a 1/2 degree of cooling. Taking Patrick's talk to heart, I can certainly imagine that there are political and societal challenges to actually be cooling or desire to cool the planet down rather than just holding temperatures constant. But even there, it would be a 1/2 degree of cooling would be at least a decade in. And at that point, we would know vastly more than we do today. And at that point, one still has the opportunity to say, either no, we don't like what we're seeing, we're going to ramp back down, we're going to hold temperatures constant, we're going to hold the amount of cooling constant, and so forth. So there's a couple of reasons for thinking through these physical scales. One is, of course, as I said, to sort of think through the uncertainties that would be resolved prior to a deployment decision. Another is to, thinking much more concretely about the research governance that's needed at different scales, rather than sort of thinking about research governance in the abstract without sort of concretely anchoring it to scale. I think rather than moving on to my next slide, I'll just talk on this one for a little bit more.
About a minute, Doug.
Okay. So there are a number of us who are starting to think about what that sort of small experiment would look like. I think if you are interested in engaging that discussion, I'd be certainly happy to talk to you. I'd point out that, I think Dan and I, in our proposal to area, we put the range at sort of 10 to 100 tons. That's sort of the range of plausible payloads of an aircraft. I would hope that we can keep that to the lower end of that scale. And just to put that in context, that's a few seconds of our current global anthropogenic SO2 emissions, or roughly 1 micro Pinatubo. I would actually argue, given how long it will take to simply plan and conduct that experiment, and the significant amount of uncertainty associated in the aerosol microphysics, that it actually makes sense to start thinking through that experiment in more detail today. And I will pass it off to the next person.
Thank you very much, Doug. So our next speaker is Jared Farley, presenting the Climate Intervention Dynamical Emulator. Go ahead, Jared.
Hi, yeah. So today I'll be presenting my work on building a dynamical, or my work and the work of my co-authors on building a dynamical emulator capable of capturing SAI's effects. Next slide, please. So the emulator is called CIDR, and to reiterate, CIDR is a dynamical emulator. So it's essentially just a reduced order model, kind of like FAIR, that mimics some behavior of a larger complex system. Emulators can be machine learning. This one isn't. CIDR mimics a particular Earth system model's time-varying responses to temperature, precipitation, and evaporation. That means any uncertainties or biases that that particular Earth system has, CIDR will inherit as part of it. For that, with that in mind, all of the stocks figures are when CIDR emulates CESM, but CIDR can also emulate UKSM, and it is partway through the training of being able to emulate E3SM. Next slide, please. So why an emulator? An emulator is a tool, and tools have to have a purpose. Initially, it was for uncoordinated deployments of SAI. And before I talk about uncoordinated, I do want to talk first about coordinated deployments. Next slide, please. So a coordinated deployment, what we mean by that is that there's one actor, and that could be a nation or a coalition of nations, deploying some form of global SAI. There's one climate goal, or there's a set of compatible climate goals, and there's generally one strategy that you're using to achieve all those goals simultaneously, and you have access to all the needed injection sites. Next slide. An example of a coordinated deployment would be, again, ARISE. ARISE is seeking to maintain surface temperature and its temperature gradients to the 2020 to 2039 baseline, or about 1.5 degrees above pre-industrial. It uses a mixture of 30 north, 15 north, 30 south, and 15 south in alternating patterns, or in controlled patterns, in order to maintain all of its targets simultaneously. Next slide. Uncoordinated deployments get a little bit more complicated. Next slide, please. A fair warning, there's a lot of text. So here is one example of an uncoordinated deployment. Philanthropists deploy Arctic SAI to restore sea ice to 2020. Elsewhere, a nation deploys at the equator to bring the world temperature down to like 2000 levels, say 1 degree above, or that's 0.5 degrees above pre-industrial. A third country notices that everything is happening in the north and the center and goes, oh, that's going to mess with the rain belt around the equator, and scrambles to deploy in the southern hemisphere to restore the ITCZ to its pre-SAI level, so before this even started. And because, nefarious actors seek to disrupt that second actor and cause a termination shock, or a rapid increase in world temperatures. To shorten this, next slide. Here are the goals shortened down. And to account here, next slide, we have a lot of different factors that all can be changed. The number of actors, what they are looking at, where they are bringing what they're looking at to, what strategy they're going to do to try and make that happen, when they start, any events that might happen to them, independent of their deployment, and when those events happen. And next slide. All of these factors affect each other, even if they aren't coordinating. So if I add another actor here, all three of these would have to respond. Next slide, please. So the main difficulties here are that there are many possible combinations, many different responses, and it's very expensive to run an Earth system model. So we turn to something simpler. Next slide, please. Here basically is how CIDR works. It takes SO2 injection, runs it through an aerosol module, and outputs AOD. That AOD gets fed into a temperature module, which is kind of like a 2 boxes, a semi-infinite diffusion, which outputs the amount of cooling. That scales some pattern to provide a cooling pattern. And then next slide. Essentially, we do this at all the latitudes that you could want to inject at, or that is covers the degrees of freedom of the amount of cooling. And we add all those patterns together to output a final total temperature pattern. And with that, we can start to mimic what we see in the Earth system models. Next slide, please. So to go back to our uncoordinated scenario, we actually ran this in CESM as well as CIDR. To recap, we have 3 different actors with 3 different goals at 3 different times, and then we're terminating one of them, the green one. We see the drop in AOD, we see the movement of temperature. The main takeaway here, there are 2 main takeaways. It does a pretty good job. It's a little off on north-south temperature gradient because, crucially, CIDR does not capture ocean dynamics, and it gets AMOC wrong. You'll hear more about that later. And for what it's worth, CIDR also captures precipitation and evaporation. Next slide. In a recent development, CIDR can be extended to capture variables which are nonlinear, like sea ice. If you have a representation of the relationship between a local temperature and the variable you care about, you can create that mapping and use CIDR's output of 1 to give you an estimate of the other. Next slide, please. And lastly, because it is so cheap to run, as opposed to a climate model, it is half a second on a MacBook Air. You can, in fact, put it on a website and allow users to be able to create their own SAI scenarios with wildly different varying temperature patterns. Next slide. So to conclude up, why an emulator? Initially, it was to look at those uncoordinated deployments of SAI. But more broadly, CIDR is useful for the exploration of SAI scenarios in general. You can expand it to focus more regionally on, or expand it to focus on more regionally specific variables. You can open it up to anybody. They don't need to have supercomputer access. Something recently that I ended up doing over at Sandia is use in controller algorithm design and providing a test bed for, say, different versions of Arise. You can integrate it live into games and workshops like we did at the Degrees Global Forum. And potentially, you could link it in with IAMs. And that's all I have. Thank you. Next slide.
Thank you very much, Jared. And you were very efficient in time. And I think you do have a couple of questions in the chat that you can take a look at. So our next speaker is David Peterson, who's going to be, I guess, talking more about analogs in terms of a worldwide inventory of pyro-CB and smoke, stratospheric smoke injection. Go ahead, David.
Okay. Hi, everyone. I'm not Dave Peterson. I'm Melinda Berman. I'm presenting on his behalf today. And I'm going to be talking about some recent results that we published, revealing the frequency and variability of pyrocumulonimbus and the smoke aerosol mass they inject into the stratosphere over the decade from 2013 to 2023. Next slide, please. So the first big question that we have is, how does this wildfire smoke interact with other sources of stratospheric aerosol injection? And so what you can see here is a plume of pyro-CB smoke injected into the stratosphere from one of the largest events that we know about from August of 2017. And you can see this is a very large plume of smoke. And an important question is, really, how does this activity compare to volcanic eruptions? The amount of smoke aerosol mass that's injected, the type of aerosols that are put into the stratosphere, and then the downstream chemistry and dynamic effects that this can have. Next slide, please. And so this is just an example of a pyro-CB. And so you see that we have this smoke plume that rises up from the lower troposphere, makes it through to the free troposphere. And then ultimately, in this example of a pyro-CB, we do end up with an overshooting top in the stratosphere that leads to high altitude smoke exhaust. Next slide, please. So we do know that there are climate scale impacts of pyro-CB smoke plumes. This is the observed record of stratospheric aerosol optical depth from OMS LP. And you can see here we have highlighted two of the largest plumes that are in this record are actually from pyro-CB. So the Pacific Northwest event in 2018 and the Australian New Year super outbreak, which happened in 2019 and 2020. And the 2019 to 2024 record features the highest levels of stratospheric aerosol optical depth during the entire Pinatubo era, or during the entire post-Mount Pinatubo era. And a significant contribution to this is the Australian New Year super outbreak, as well as additional pyro-CB smoke injected into the stratosphere in the Northern Hemisphere during the seasons of 2020 to 2023. And so what this tells us is that pyro-CB are in fact first-order drivers of variations in stratospheric composition and structure. And because these are not really well taken into account in global climate models and other radiative forcing mechanisms and feedbacks, we really need to understand the role that they play on a global scale to be able to properly account for the role that they play in the climate system. Next slide, please. So in addition to kind of these large scale aerosol effects, we also know that pyro-CB smoke can affect dynamic circulation and ozone. So absorbing smoke layers can generate anticyclonic circulations in the lower stratosphere. There's rapid vertical transport of these circulation anomalies. This can displace local ozone. We know that smoke is also able to induce dynamic perturbations and generate anticyclonic rotation. And anomalies of stratospheric ozone can occur from heterogeneous chemistry on these smoke particle surfaces. So not only are we seeing kind of these large scale impacts from a radiative forcing perspective, excuse me, but there's also stratospheric dynamical implications as well as chemistry implications. Next slide, please. One more as well, please. Thanks. And so here's 3 examples of the effect of the Australian New Year super outbreak, where you have this large plume of smoke on the left that continues to rise into the stratosphere, as well as inducing UVAI anomalies measured by OMS, as well as potential vorticity and circulation anomalies in the stratosphere. Next slide, please. So an important step in answering this question about the role that pyro-CB play in the climate system and the magnitude of these impacts is we need to be able to actually quantify pyro-CB and the effect that they have. And so a recent paper that was just published and is now out in MPJ Climate and Atmospheric Sciences looks to address this question. We have the Naval Research Lab's Worldwide Pyro-CB Inventory from 2013 to 2023. And the first question we looked at is, where do pyro-CB develop and how common are they? And so over this record, we were able to identify 761 confirmed pyro-CB with 5 main regions of activity: Canada, CONUS, the continental United States, Northern Asia, Australia, and Alaska. And you can see a density plot of where these pyro-CB occur here. Next slide, please. So here are the regional and yearly distribution of pyro-CB activity over the period that we analyzed. And you can see, by far and away, Canada leads our regions with the most pyro-CB activity with 350. And when we look at the yearly distribution of pyro-CB activity for this distribution, we do see a large amount of variability with 169 in 2023, but the year before, 2022, only had 44. So there is considerable interannual variability in the amount of pyro-CB that occur, and thus the amount of stratospheric aerosol smoke that there might be. Next slide, please. When we extend this out to 2025, we do see that there continues to be large amounts of pyro-CB activity. So we're still well over the 100 pyro-CB year mark with 112 and 121 in 2024 and 2025 respectively. Next slide, please. So now that we have a handle on where pyro-CB occurred, the next question that we had is actually to be able to determine the smoke injection altitude of pyro-CB have to understand how many pyro-CB events are putting smoke into the stratosphere to ultimately answer the question of how much smoke is going into the stratosphere. So this figure on the left shows the maximum smoke injection altitude in kilometers, and we can see that that most of our events are within this 10 to 12 kilometer injection range, but we do ultimately see events that are injecting smoke well over 15, 16 kilometers in altitude, all the way up to 18 kilometers. And when we break this down into an injection altitude relative to the tropopause, into a tropospheric, near tropopause, or stratospheric category, we do see that 55% of the events that we looked at, or that we analyzed, had smoke injections within 1 kilometer or greater of the tropopause. And so that means that a significant amount of the pyro-CB events that we see are actually putting smoke into the stratosphere or in the near tropopause region very close to the stratosphere. Next slide, please. However, we've done all this work, but there are still a lot of unknowns about pyro-CB from the surface, including the characteristics of the contributing fire, what type of materials is it burning, how those materials could impact the chemistry that occurs, all the way up to the stratosphere. And so this high altitude smoke exhaust, what are the rules for secondary aerosols when the precursors are existing much higher in the atmosphere? How does this influence ozone chemistry? And then really the impact of pyro-CB smoke on regional and global scale radiative forcing. So there's lots of outstanding questions that we have. Next slide, please. To answer some of these questions, NASA has recently funded the INSPIRE project, or Injected Smoke and Pyrocumulonimbus Experiment. The hypothesis for this project is that increasing wildfire size and intensity will amplify pyro-CB-driven smoke injection into the stratosphere, resulting in measurable changes in Earth's radiative balance. You can see the 3 main science questions on the right as well, and there are 3 main platforms that INSPIRE will be using: remote sensing at high altitudes via the ER2, in situ observations from the NCAR NSF Gulf Stream, and then ground and mobile-based observations as well. Next slide, please. So this is just an example of the airborne measurements that they plan to do in INSPIRE, where they're sampling air above the smoke plume. They'll descend down into the smoke plume and then below the smoke plume as well in the UTLS. Next slide, please. So just to wrap everything up, if you have any questions, feel free to ask me or feel free to reach out to Dave. Our worldwide pyro-CB inventory, which is available as the supplementary data in the Nature paper, is important for understanding the role of pyro-CB in the Earth system. We know that at least 55% of the pyro-CB in the inventory injected smoke within 1 kilometer or higher of the tropopause. And these events on an aggregate level, so on a regional level or on a yearly level, do amount to the same amount of stratospheric aerosol mass being injected on the order of a volcanic eruption. And individual events in and of themselves can also inject the same amount of smoke in the stratosphere as volcanic eruptions. And two of these events are the Pacific Northwest event and the Australian New Year super outbreak. And we see that these individual events, as well as the cumulative effect of pyro-CB, can really play a large role in altering the amount of aerosols in the stratosphere, the dynamics of the stratosphere, the chemistry of the stratosphere. However, there are a lot of unknown questions that remain to be answered with pyro-CB. Thank you.
Thank you, Melinda. Very interesting. And our next speaker is going to be a recorded talk. So I think Liwa has to bring that up. And it's by Walker Lee. And it's talking about the ARISE experiment, looking at different pathways with G2 SAI. So can you bring that up, Liwa?
Hello, everybody. My name is Walker Lee. I work at the National Center for Atmospheric Research in Boulder, Colorado. I'm sorry I couldn't present in person today, but I'd like to thank the conveners for allowing me to record my talk in advance. Today, I'm going to talk about a modeling experiment we did called G2 SAI and what we learned about the ARISE SAI 1.5 experiment. So many of you are probably familiar with ARISE SAI 1.5, which is a modeling experiment first published in 2022. In the mid-21st century, against a moderate warming background, stratospheric aerosol injection is used to maintain a temperature target of approximately 1.5 degrees above pre-industrial, and injection rates at 4 different latitudes are managed independently in order to control for not only the global mean temperature, but also temperature gradients called T1 and T2. This injection strategy and scenario has become very popular and widely studied in the past 5 years or so. And so my colleagues and I wanted to explore this kind of injection strategy in further depth. And so we designed an experiment we're calling G2 SAI after the original G2 experiment proposed by the Geoengineering Model Intercomparison Project, or GeoMIP, in 2011. In the G2 experiment, against a control background, annual 1% increases in CO2 concentrations are offset by decreases in the solar constant. And we are revisiting that experiment, but instead of using solar dimming, we are directly simulating a contemporary stratospheric aerosol injection strategy, similar to the one used in ARISE SAI 1.5. And by simulating this injection strategy against a stable background with no anthropogenic changes, we can hope to better understand the impacts of the aerosol injection. Our first simulation had an injection distribution that looked very similar to ARISE SAI 1.5, where most of the SO2 was placed at 15 degrees south latitude. And this is because in this model, injection at 15 degrees south cools the planet relatively evenly. However, because these simulations are much longer than ARISE, 150 years compared to 35 years, we wanted to run an additional simulation where the controller had more freedom to adjust its injection strategy over time to see if it would change. And it did. In our second simulation, our controller transitioned to an injection strategy that placed much less at 15 degrees south, and most of the SO2 went to 30 degrees north and 30 degrees south. And we think we understand why this happened. If we look at the temperature maps for our two simulations, our first simulation that we ran, where most of the SO2 went to 15 degrees south, we see a substantial patch of cooling just south of Greenland, which is strongly indicative of a decline in the AMOC, Atlantic Meridional Overturning Circulation, which carries warm water from the tropics to the North Atlantic. And in our second simulation, we don't see that cooling patch south of Greenland. And this is corroborated by directly measuring the AMOC strength in our simulations. And our results are very consistent with past literature on how stratospheric aerosol injections in different hemispheres affect AMOC strength differently. And so what we have are two simulations with the same temperature targets, but they have two distinct stable climate states, where our first simulation has a weaker AMOC, which means less warm water is being carried to the North Atlantic, which means there is a cooler northern hemisphere, a smaller T1, and therefore less need for injection in the northern hemisphere, which in turn encourages a weaker AMOC. In our second simulation, we see the opposite, where we have a stronger AMOC, which encourages more injection in the northern hemisphere, which in turn encourages a stronger AMOC. After seeing these results, we wondered if ARISE SAI 1.5 could have looked any different. The first 10 ensemble members inject mostly at 15 degrees south and do slow the decline of the AMOC, but do not stop it. And so we ran 3 more ensemble members of ARISE SAI 1.5 with the same T0, T1, T2 temperature targets, but the control algorithm encouraged more injection at 30 degrees north and 30 degrees south and met the same temperature targets. And there are, even though the simulations are relatively short, only 35 years, there are statistically significant differences between our new ARISE simulations and the original data set that can be explained by the differences in injection strategy. Our new simulations have a warmer North Atlantic, suggesting that AMOC is indeed stronger, and there are other differences in surface temperature and precipitation between the two data sets. We don't necessarily claim that one is better or worse than the other, just that ARISE SAI 1.5 indeed could have looked different if the injection strategy was different. And so in summary, our G2 SAI simulations reached 2 distinct climate states, and we revisited ARISE SAI 1.5 and found an alternate solution to the control problem that yielded statistically significant differences after just 35 years. And this has implications for how we design and analyze stratospheric aerosol injection experiments, especially those using the T0, T1, T2 framework. Thank you.
Okay, well, since Walker isn't here, you can't directly ask him questions, but one of his authors is here, Simona. So if there's any specific questions on Walker's talk, go ahead and address those to Simona. And we're now going into a short discussion period that can cover any of the talks in this session. And I'm just going to highlight right now in the chat, Seb Easton had some questions to Patrick Keys, and I was wondering if Seb could elaborate on that and maybe talk a little bit about that discussion so everybody can hear what was going on.
Sure. Thank you. And thanks, Patrick, for the talk. It was really, really fascinating. So the question was, if I understood it correctly, there's this concern about the degree to which a perceived failure of SAI might have implications for SAI as a whole and for how it's perceived by society. And it occurred to me that that might have some implications for how SAI at different rates is perceived. For example, a very rapid introduction of SAI might have a larger likelihood of a perceived change than what I think we would generally think of as a safer, slower introduction. So I'd love to just get your thoughts on that, Patrick, recognizing that that might be a bit much for a quick Q&A.
Can you hear me? I can't tell if you can hear me.
Yeah, we can hear you.
Okay. Yeah, it's like I made the comment in the chat that it's probably too much for a workshop comment and response. But I think that this is true of any type of SAI deployment. It's also true of net zero achievement, where natural variability is just going to mask a lot of smaller scale temperature changes, either unintentional via climate change or intentional via SAI. And this is where, the community has been thinking about social scenarios for a long time, political scenarios, et cetera, but I think we have to almost expand that to include almost behavioral perception, the psychology of this, also to understand how would this land. And I think, just taking the United States as an example, every 4 years almost, there's a different political party in power, and that matters quite a bit for policies, what happens, what environmental agencies are even funded to do. And so this gets to a lot of questions around governance and so forth. And I'm not sure, I mean, rates of deployment would matter quite a lot. But I think as much as the rates matter, it's also the time lags of detection and perception of those time lags and how quickly detection and perception translates to policy enactment. Which those would be related. If it was a really pronounced rate versus very modest rate, then yeah, you could see probably a different time scale associated with the perception feedback. But yeah, I think as much as that's important, it's also baking in psychology and understanding that a bit more. Thanks for your question.
Thank you, Patrick and Seb, for elaborating on that. It is a very complicated issue, and I think it kind of relates to, there was a comment in the chat by James Fleming that I don't think the entire audience saw, where his comment was, do any of the speakers take the work of Ed Lorenz seriously, where he's basically talking about, the butterfly effect, what is internal variability and what causes that. And so we're trying to do something, or talking about doing something that is concrete, making changes on top of internal variability, where you look at the global average, you see one thing, but if you're sitting in, I forget who showed the plot of Beijing, 4 different scenarios where you have different temperature things going on. And when you're looking at one spot on Earth, it's going to be very difficult to convince the populace that what you have deployed is actually going to do something. And so then we still have a few more minutes. So does anyone else have anything they want to bring up? Go ahead and raise your hand, or if any of the panelists want to say anything. We have 5 minutes. I think some of the if not, we can bring up some of the other questions that were answered.
There are 3 hands raised in the.
All right.
We do have some people with hands raised. Ron, Simone, and Jean-Paul. Thank you.
Why don't we go with Jean-Paul?
Yes, Karen. So I had a question for Doug here. I mean, we have seen several talks during that session which are promoting small-scale SAI deployment or SAI deployments. And it's very controversial. And there is a company in the US called Make Sunset, and someone talked about it yesterday that is already deploying some balloons. And so the question was to Doug was, is there anything we should try to do about it, and we can learn from those activities of Make Sunset?
I think a couple of comments on that. One is, I think the Make Sunset's activity is too small to actually be useful from a scientific perspective. I also, I don't think they should be doing anything at all. And so I would hate to actually give them cover to suggest that what they were doing had any value. I actually think the issue to me at some level is simply, we're doing all of this work thinking about what the effects would be. We have huge uncertainty in the aerosol microphysics. And on top of that, what we have for validating that comes from volcanic eruptions that may be a very imperfect analog of releasing material from an aircraft.
Thank you, Doug.
Okay, why don't we take the question from Gregory Slater has his hand up. I think you're set up so that you can talk.
Thank you. Can you hear me?
Yes.
Thanks. My question was for Wake Smith, and it's about what I took as pessimism about actually any cooling in any implementation of global SAI, that the amount that would be required would be so large that it's almost prohibitive, and your scenarios involve more maintaining maintaining a cap temperature at some point, but no cooling. Is that a misrepresentation of what you were saying?
Say that it's prohibitive, but I imagine it would be prudent to start small and ramp up slowly. And the first bit of ramping up might merely be to slow or halt the warming. Whether the world gets so enthusiastic about this that it wants to begin to actually cool the planet is farther down the road, and maybe we don't need to speculate about that now. I don't think that's likely the way that one would start. But maybe I should clarify that I'm making my own judgments here. In this response to you, I'm not describing any physical constraint. If the world really wanted to cool itself, presumably that's an objective that could be set for SAI, but I think it is a sort of extreme objective that we should evolve to rather than commence with.
Thank you, Wig. And I'm gonna, let's end this. Simona has her hand up, so go ahead and make your comments, Simona.
Okay, yeah, I had a question for Wake regarding high latitude injection, but it's also about starting injections or experiments right now, in particular for potential polar injections. So that's came about when I saw the talk from the PyroCB. So we do know that our models can still improve, and we can still do a lot of experience, also learn from volcanic eruption and PyroCB. And seeing now that, I mean, knowing that there is a lot of injection of dust and other particles in the lowermost stratosphere, which is aligned with the place where you would start polar injection. I wonder if anybody even had looked at that combined event at this point, or if we shouldn't do first model simulations before we think about those, field experiments. And that's also to Doug.
Yeah, I'm going to say I think that's more nearly Doug territory. I sure have not looked at that.
I mean, I actually think, to me, I would still say we should unequivocally learn what we can from the natural analogs first, and I'm not convinced that those have been fully mined. I don't think that those would be sufficient. And I do actually think if simply because I think that the release from an aircraft where you're after the initial wake mixing, you've now got SO2 in a region that's a couple hundred meters across, which is vastly smaller than the plume of either a volcano or PyroCB. And so it's very unclear what physics, what the competition between coagulation and nucleation condensation and nucleation when you get a new molecule of H2SO4, sort of unclear how that competition works when you're on a much smaller spatial scales. Having said that, to the extent that there's nonlinearities associated with whatever the background aerosol concentrations are, might actually make a lot of sense to do that experiment in a PyroCB plume rather than in a quiescent part of the stratosphere, and basically understand more about how the nonlinearities evolve there. I don't know if that quite answered the question, but
it gives things to think about.
Yeah, I would say this is still in the thinking stage, right? I think we actually need all of this discussion, and we need much broader sort of community like poking and thinking about what makes sense to do before one goes and says we're definitely going ahead.
Great, thank you, Doug. I just want to bring up that on Thursday and Wednesday, we have a lot more time for open discussion, even though for some of you it's in the middle of the night. I would still encourage you to join if you're interested in contributing to this. And we will now take our short break and end up the day with SAI impacts on chemistry, health, and the economy. Thank you.
Right. And I think the short break seems to be only 1 minute. Is that right, Mark? Or should we give people a little bit more time?
Yeah, let's keep the break 3 minutes so people can do whatever they like.
And then meet at 33 minutes after the hour.
Yeah.
Is that correct?
Then
okay.
We have a 3-minute delay. I think we can cope with that.
Yeah.
Okay. Thanks.
Thanks.
All right, I think people are slowly coming back to the last of our session for today. And to the next set of 5 talks starts with Etienne Giljian, I hope I say that right. Impacts on ozone from interactions between sulfate SAI and potential future halogen sources. Please go ahead.
Hi, can you hear me? All right.
Very quiet, I guess.
Oh, try to speak a bit louder.
Okay, that's good now. Yes.
Okay, great. So first of all, I'd like to start by thanking all the people mentioned in these slides for helping tremendously with this work and like also introducing me kind of newbie to this field. So thank you very much. So potential future halogen sources, what do I mean by that? So if you go to the next slide, please. I mean, 2 things. The first one is rocket halogens and then also volcanic halogens. And why do rocket halogens matter? Because right now we don't have that many of them in the atmosphere, but this is the number of orbital launches is steadily growing every single year. And so here you have on the first figure, this is a rather conservative estimate even. So about like 600 launches by 2030. We can go like up to, there are worse scenarios where we get almost 2,000 launches per year for 2030. So this might become a rather significant source of halogens, and these halogens also get propagated throughout the whole atmosphere because, well, rockets, they go through the whole atmosphere. And it's also important to note that not all rockets release halogens, but mostly the solid booster fuel. So if you go to the next slide, please. So what we did was simulate 4 different scenarios in so-called V2, and this was a time slice experiment of 30 years. So the reference scenario, we took projected 2060s condition. The SAI scenario, we used 5 teragram of sulfur injected at plus minus 30 degrees. For the reference rocket scenario, we used the reference scenario with added gas phase rocket emissions according to the 2019 launches, but scaled up to 2040 launches per year. And in the last scenario, which is SAI work, we just have both emissions from SAI and the rockets. So next slide, thank you. First of all, we wanted to like check the model that everything works well. So this is only the SAI results. And on the left, you see the latitude ozone anomaly throughout the year. And we obtain an increase of several tens of topside units in the north and a decrease in the south, which is quite within the expected range. And on the right, you see like more precisely some of the processes, and there are 2 that I'd like to highlight as they will become important later. The first one is the strengthened vortex in the southern hemisphere, and the second one is the increased transport and also weakened vortex in the north. Next slide, please. So this is the rocket impact. On the left, you see the rocket impact on the reference scenario, and on the right, under SAI. And so we see, first of all, that there is a general decrease of ozone overall between like 1 and 10 hectopascal, which is as expected and confirms previous research. And now the new things and the big result that we have is that the halogens from the rockets will actually really worsen the problem over the South Pole, also because of the increased vortex there, which will keep the chlorine there for longer, and the increased chlorine activation from the SAI will also worsen the problem. In the north here we see an increase, but this is much harder to be confident about because the model is quite susceptible to very small changes here. So we are not entirely sure, or at least not confident enough to say that this is something that will happen. In the south, this is quite stable over almost all versions that we did. So if you go to the next slide, please. We also did some volcanic simulations because we thought halogens from rockets are bad. What's another source of halogens? Well, volcanoes. And so we did the same scenarios, except we don't have rocket emissions, but we have a volcanic eruption. So we used 6 teragram of SO2, and so this is about Pinatubo sized, and 0.84 teragram of HCl, which is a rather high co-injection. So 14% is the upper end of estimate for Mount Mazama, but this is at first just to try to see what would happen in extreme scenarios. And we simulated each time for 5 years. So if you go to the next slide, please. So the top one is this eruption under reference conditions, and the bottom one under SAI. And for the top, you see that this is basically the same result as the SAI. So we have an increase in the northern hemisphere and a decrease in the southern hemisphere, which varies seasonally. But under SAI conditions, we see that the effect is actually flipped in the northern hemisphere. So there, the chlorine effect will actually take over, and this will result in a net decrease of ozone overall. And this effect is also visible for lower co-injections, so 10 times less HCl. But then in the northern hemisphere, it doesn't lead to a decrease, but just stays about 0. So this effect also exists there. And if you go to the next slide, please. So general, we can say that any halogen sources in sulfate SAI conditions will amplify the negative effects on ozone. So this is something that we will need to think about, where if we implement SAI, what will happen with rockets? Should we maybe just change fuel types or something else? And generally also the southern hemisphere response is pretty clear and linear, and it works well. The another one is linked with much more variability and uncertainty. And that's all from my side. Thank you very much.
Thank you very much. Very well on time as well. Our next speaker is Sandro Battioni. I think you will share yourself, maybe, Sandro? And talking about better constraining kinetic parameters of HNO3 and HCl uptake on calcite particles by lab experiments. Sandro, please.
Yes, hello. Can you hear me?
Yes, we do. And we see your slides, please. Yep, it's on slide mode.
Perfect.
Bye.
Okay, yeah. I will talk on, hello everyone, I will talk about the heterogeneous chemistry on calcite particles. Calcite particles are suggested as an alternative to sulfuric acid aerosol for stratospheric aerosol injection due to their potentially better physicochemical properties. So calcite particles, or calcite, is a base. It can react with the acids in the stratosphere, which are mainly HNO3, HCl, and H2SO4. The acids could be taken up on calcite particles, and this would then form these salts at the particle surface. Yes, so what would happen if we take up or if HCl would be taken up on the particles? That would form calcium chloride, and the chloride would then be removed from the stratosphere via sedimentation on the particles. So there would be a reduction of HCl, so a reduction of chlorine, which would increase stratospheric ozone concentrations. So this potentially could fasten up the healing of the stratospheric ozone layer by removing chlorine from the stratosphere if HCl uptake would be efficient. However, on the other hand, if we would take up a lot of HNO3 on the particles, that could reduce stratospheric ozone concentrations due to the reduction of NOx concentration, which would then result in a deactivation of chlorine and reduced ozone concentration. There have been previous studies which looked at the uptake coefficient of these acids on calcite particles. The uptake coefficient is the fraction of collisions with a surface that lead to a reaction. And as you can see, the uptake coefficient for these two acids on calcite range over several orders of magnitudes for previous experiments. And uptake coefficient of 10 to the minus 1 would relatively fast, like within minutes, deplete the stratospheric reservoirs of the whole of these acids, while uptake coefficient of 10 to the minus 6 or smaller would not do much to stratospheric chemistry. So it's now very important to really quantify the uptake coefficients under stratospheric conditions, and also to look at the potential passivation effect. So as you can see here on the left on the figure, the acids, when products are formed at the surface of the particles, the interior of the particle might not be available for further reaction when the interior is efficiently sealed off from the products at the surface. So that would lead to passivation with time. And this passivation effect needs to be considered when looking at heterogeneous chemistry or at the uptake of these acids on calcite surfaces. And that we did with two techniques. So we really looked at the surface composition when exposing calcite samples to those acids, HNO3 here depicted here, at stratospheric conditions in terms of partial pressure, temperature, and relative humidity, and also as a function of time. So we used two measurement techniques: heavy ion elastic recoil detection analysis. This is based on the recoil of ions, which and therefore allows to measure the elemental composition of the sample to depths 200 to 300 nanometers below the surface. But it's an ex situ technique, which means that you need to pre-process the sample and then put it in the measurement cell and measure it. And on the other hand, ambient pressure X-ray photoelectron spectroscopy is an in situ technique, so it allows to really in situ dose these conditions and measure the sample or the composition of the sample while dosing, but only over the upper 2 to 3 nanometers. First, I show some results from heavy ion ERDA. This is the reference sample. As you can see, it can represent the basic composition of the calcite. It's like 60% oxygen, 20% calcium, and carbon. So now we expose the sample to 0.8 ppm HNO3. It's about 100 times stratospheric concentrations, and that for 10 days at 250 Kelvin. And you can clearly see a diffusion-like profile at if you go from the surface here at the left toward the depth. And there is a composition of up to 3% nitrogen throughout the upper 50 nanometers. From this, we can derive diffusion coefficient of about 10 to the minus 17. Now we have increased the concentration by a factor of 10, 8 ppm HNO3, same conditions otherwise. So it's 1,000 times stratospheric concentrations for 10 days. And you can see that the uppermost 200 nanometers completely got converted to calcium nitrate. There is no calcium carbonate anymore, so no carbon in black anymore throughout the whole surface. And there is also a lot of water now in the sample, which points at the crucial role of hydrates at those conditions. And after we stored that sample for 10 days in vacuum, we did another measurement of the very same sample, and surprisingly, we saw suddenly the calcium carbonate came back. It diffused towards the surface from the sample interior, so there are strong diffusional processes, exchange of nitrate and carbonate in the sample, and this points to strong diffusion processes in the sample. Now let's have also a look at the ambient pressure XPS measurements. Those the setup, we use the setup at the Swiss Light Source at Paul Scherrer Institute, and the setup there allowed for the first time to really measure in situ with stratospheric concentrations of HNO3 at stratospheric temperatures and humidity, the uptake of HNO3 on calcite over several hours, up to 1 day almost. And you can see that at these conditions, at between like 0.6 and 17.6 times stratospheric concentrations of HNO3, the effective calcium nitrate thickness that reaches values of up to 2 nanometers. And from this, we could calculate uptake coefficients, which range between 10 to the minus 4 and 10 to the minus 5. And most importantly, you can also see that the uptake decreases with time in almost all measurements, which points at the passivation with time. We now put all our measurements here in green from ERDA and XPS into a plot with all previous measurements of the uptake coefficients of HNO3 and HCl. And as a function of the exposure. And the exposure is the concentration of HNO3 and HCl times the duration of the experiment. That's the expression for the exposure. And there is a clear trend which could be observed, like particles freshly exposed to the stratosphere or to HCl and HNO3 start with a very high uptake coefficient, and then with time the uptake, or with increasing exposure, the uptake decreases more and more. And if we now look what this means for stratospheric exposures of HCl and HNO3 of calcite particle, assuming a residence time of 1 year in the stratosphere, we would arrive at values of about 10 to the minus 5 for HCl and 10 to the minus 4, roughly 10 to the minus 4 for HNO3. Yes, and so these values we now put into our aerosol chemistry climate model, so-called AR, looked at the effect which would result on stratospheric chemistry, on ozone more specifically. And you can see that there is not a big change in ozone. There is at most 2% increase over the southern polar region. And as a reference, we also show the SO2 the injection response, the response of ozone to SO2 injection, which is substantially more. However, as you've seen in this plot, the uncertainty ranges are rather large, so we cannot exclude higher uptake coefficients of up to 10 to the minus 3 before passivation hits in. And we also did sensitivity analysis to those higher uptake coefficients, and with the uptake coefficient of 10 to the minus 3 for HCl, you would substantially heal the ozone hole, and ozone concentrations would increase up to 25% in an annual mean for an uptake of 10 to the minus 3 for HCl. On the other hand, uptake coefficient of 10 to the minus 3 for HNO3 would result in substantial ozone depletion of up to 10% over the poles. And yeah, to conclude, these are only two heterogeneous reactions, to say. Uptake of HCl and HNO3. It's most likely not a significant impact on stratospheric ozone, but more research is needed to better constrain these quantities. And there are also other heterogeneous reactions that could occur on calcite surface, which also needs to investigate it in the future. And with this, I want to finish. Thank you very much for your attention.
Yeah, thank you very much. Very interesting talk. We go right to the next speaker. We will have Cindy Wong now, and she will talk about air quality impacts of stratospheric aerosol injections. Air quality impacts are small and mainly driven by changes in climate, not deposition. Okay, Cindy, please go ahead.
All right. I hope you can all hear me okay. Yeah, my name is Cindy. I'm relatively new to the field, so I appreciate the organizers for organizing this and giving me an opportunity to give this talk. Next slide. So I don't think I have to go in depth about explaining what SAI is to this community, since we've had a plethora of talks discussing it. But the objective of this work was to look at the potential impacts of SAI on air quality, and particularly looking at changes in PM 2.5 and ozone. And also, I'm not going to be focusing this much on the talk, but in the preprint, we also discussed a little bit about the internal variability and the role it plays in shaping the impacts of SAI on air pollution. Next slide, please. So the simulations we're going to be using are 3 CSM Wacom 6 simulations, each with 10 ensemble members. So the ARISE simulations follow the SSP2 4.5 simulations, but include injections in 4 locations to maintain temperatures at either 1.5 or 1 degrees Kelvin. And the next slide, please. And so to start off with our analysis, we want to look at how particulate matter in ozone changes are happening. And so we're going to be presenting this in 3 ways. The first column shows the changes under SAI implementation. The second one shows the changes under SSP2 4.5 pathway without SAI. And the third column compares a future with SAI to one without. So I'm going to be drawing most of the emphasis on the third column and the responses. But ultimately, when we look at PM 2.5 changes between the ARISE SAI 1.5 and SSP2 4.5, we see that there is some sort of correspondence to the regional changes in precipitation in some regions, but not others, which indicates that in particular, in regions over Central America and Central Sub-Saharan Africa, the precipitation changes align, but in other places, circulation, vertical mixing, or aerosol cloud interactions may be contributing to changes in PM 2.5. And so while I'm not going to show this, we also do find that dust and secondary organic aerosols contribute to the PM 2.5 changes rather than sulfate changes. Next slide, please. And now, so looking at Osmata 8, which is a metric that's used to look for long-term exposure of ozone, what we find really interesting is that in the last column, we see that because in this scenario, SO2 is injected primarily in the southern hemisphere, we find that this leads to a sort of hemispheric asymmetry and a stratospheric ozone response that leads to tropospheric ozone changes. How SAI impacts ozone is due to a complex variety of factors, but ultimately we find that what's responsible for this hemispheric asymmetry is different in the northern hemisphere versus southern hemisphere, in such that one hemisphere it's affected by the stratospheric exchange, but then on the other hemisphere it's affected by the surface temperature cooling effect. Next slide, please. And so now we've looked at the regional changes of the particulate matter in ozone. We can now dive into looking at quantifying exactly the ozone related and PM 2.5 related mortality, which is what I'm showing you here geographically. And looking at this, we find that the changes in mortality associated with SAI exhibit spatial variability, which are driven by regional differences. In particular, you see for the ozone-related mortality, you get this hemispheric asymmetry that's reflected in the fact that countries in the northern hemisphere are going to experience an increase in ozone-related mortality, while it's the opposite in the southern hemisphere. And so with these spatial variability, one other question we could look at and think about is, now that we see some spatial variability, how does that translate to the global aggregate of the ozone and PM 2.5 related mortality? In other words, how is that going to change? So next slide, please. Oh, sorry. Next slide, please. Oh, sorry. Can you go the slide before? I didn't, okay. Oh, I guess, sorry, next slide. I guess it's not showing up. Okay, yes. What's shown here is the global aggregate. And what we see, I'm drawing attention to the green and blue lines. Here I'm showing the mortality, the global mortality changes for ARISE SAI 1.5 and 1.0. And what we do see is that overall, over time, there does not appear to be any significant trend with the scaling of the ozone-related and PM2.5-related mortality for these two scenarios, which also have different injection rates as well. So that's something to consider. Next slide, please. So to end my talk, I'm just going to leave this up here, but ultimately what we do find, and I think the preprint discusses this more in detail, but we find that overall there are modest reductions in pollution-related mortality associated from SAI, and also the related mortality does not scale with SO2 injection rates. And something that's important to note, this caveat is actually I found out a few weeks ago when I presented this at Cacti, and Simone actually corrected me that tropospheric photolysis rates are actually not fixed. So it's always good to present at conferences and get people's feedbacks on the work. But I want to conclude that ultimately SAI can shift the spatial distribution of ozone and particulate matter, but the dominant driver of future health outcomes still remains the strength of the implementation of air quality policies. Next slide, please. Okay, I'm going to end it there, and the preprint is up if folks are interested in learning more. Thank you.
Thank you. Great presentation, well on time. And now we go over to Alice Wells, an open access workflow to assess the health impacts of air quality under climate intervention. Alice, please go ahead.
Thank you, Simona. Yeah, I'm going to be chatting to you guys today about this open access workflow that we've created to try and, similarly to Cindy, try and assess mortality impacts of air quality under different climate futures, but also in this situation under climate intervention. Next slide, please. So a little bit of background. Air pollution from surface ozone and PM2.5 is a major global risk factor for mortality. This is a figure from the Global Burden of Disease. It's like the largest effort to quantify trends in health. It's kind of like the IPCC of the health world. And it combines a mixture of exposure, so population exposure, and the level of risk due to, in this case, surface ozone. So the red colours are areas of high population with high risk, and the areas in blue are sort of low population regions with lower risk. Next slide, please. And this is just the same, but for PM2.5. Next, please. So this is important because in 2021, it's been estimated that approximately 500,000 people died due to ambient ozone pollution. And PM2.5 is actually now the second most deadly health risk worldwide. Next slide, please. So from an epidemiological standpoint, epidemiologists perform these cohort studies to try and understand the relationship between exposure to these air pollutants and mortality risk. And again, these are from the GBD. They're kind of summary figures to show how the risk might change with relation to exposure to ozone on the left and PM2.5 on the right. Now, GBD provide these actually more specific cause relationships. They're called exposure response functions, by performing a literature review of a series of studies to try and then provide this summary relationship based on very specific outcome mortalities that they believe are really confident in that relationship. So for ozone, for example, that might be mortality due to chronic obstructive pulmonary disease, and with PM there are several relationships, but including stroke, lung cancer, etc. Next slide, please. And if you want to click through, there are a few papers that will pop up on the screen. So these exposure response functions, if you could just click through the slides, thank you, are applied in health impact assessments. And there are a series of papers that have done this, and however, there can be some barriers. Next slide, please. And next, a few more times. Thank you. There's just two more, that's it. And so, yeah, and there are some barriers for this analysis. So from an epidemiologist point of view, for example, wrangling the climate model data into the particular variable that's necessary, whether that's for a short-term exposure or a long-term exposure, can be quite challenging. But also from a climate science perspective, it can be quite challenging to bring all the pieces together for these health impact assessments and applying the exposure response functions in the correct way. Next twice, please. And one more time. Thank you. So that's why we've created this open access workflow to try and help calculate mortality due to surface ozone and PM2.5. So the idea is that you could take your climate model data or even your global chemistry transport model data and input that, and it will be processed in such a way that's relevant for the particular exposure response function that we are applying. And the exposure response function is then applied for the relevant metric and mortality is calculated. And the hope for this is that it's going to allow for more interdisciplinary work and facilitate the sort of combination of epidemiologists and climate scientists together to perform these analysis, and also for research reproducibility reasons. Now, I mentioned the global burden of disease and their specific exposure response functions. So the reason we use those here is because the global burden of disease have these really confident metrics for relationships between ozone mortality and PM2.5 mortality. And sometimes bringing together these components can be challenging, which is why we wanted to bring it all together so that people can then very quickly and simply apply this workflow to their data and perform this analysis. Also, one of these reasons is that often when epidemiologists and climate scientists come together to produce these kind of analysis, they sort of stop at the end of this is what happens to mortality. But kind of like what Cindy's been doing, what will be really beneficial is for climate scientists to then be able to go back and really understand what's driving those changes in mortality, which is why it's really great to be able to combine these disciplines together. And we will be also sharing a tutorial on how to use this workflow when this is published. Next slide, please. So I'll just finish with some preliminary results with climate intervention work. So this is looking at COPD mortality due to surface ozone in both UK ESM and CESM under the G6 1.5 SAI scenario relative to the SSP2 4.5 baseline. And you can see immediately that the responses in mortality are quite different, which again is just very much simply due to the distribution of surface ozone. But I really wanted to hammer home that these responses are going to be quite different based on the climate model and also the scenario. Next slide, please. So yeah, any questions you might have, please feel free to shoot me an email or drop in the Q&A. Thank you.
Thank you very much. Very interesting as well. And now we are going to the last talk of the day, which is by Olivier Boucher, Optimizing PV Production under SAI.
Thank you, Simone. Thank you to the organizers, and nice to see you all tonight. So I'm going to talk about the impact of SAI on solar PV production. Next. Building on a couple of previous studies by Chris Smith, 2017, and Suzanne Bohr in 2024, on trying to overcome some of the limitations of these studies. Typically what I call the syndrome of the isolated panel, just to assume that there is a single panel with no shading effects. That may be true for rooftop panels, but not for PV farms, where you really have to account for shading effects from one row to the next. And also the assumption that both studies make that the optimum panel tilt is equal to the latitude, and that assumption is just not verified. In fact, the optimal tilt depends on latitude, ground cover ratio, cloudiness, and as you can see down on the picture for a farm near Paris, where the latitude is 48 degrees, the tilt is much less. Next. So we're looking at three popular PV configurations. The first one is south-facing fixed panels, which is characterized by two parameters: the ground cover ratio, which you can think of the ratio of the ground that would be covered by the panels if they were laying flat on the ground. That's also the width, the panel width divided by the row-to-row pitch. And the second parameter is the tilt of the panels. The second configuration is the east-west panels. They're much more horizontal. They're producing less at noon and more in the morning and afternoon when the electricity has got more value. They're also characterized by the GCR and the tilt. And then the third configuration is the horizontal axis panels with the panels are rotating along a north-south horizontal axis. And then there is only one parameter, which is the ground cover ratio. Next. For this last configuration, you have to account for tracking and backtracking. So tracking, as you can imagine, is that the panels are adjusting the tilt so that the sun rays are perpendicular to the panel so as to get the maximum radiation. But at some point, that triggers some shade, and then the panels are backtracking. So that's something we include in the model, and that's what happens in the field, in the PV farms. Next. So now we consider one site, which is close to the Paris region, 48 North. We have some good data there. One particular year, 2024, we have an hourly temporal resolution. We have our own PV model with the shading effects. And then we look at two scenarios. One is a present day scenario, which relies on some satellite data for direct and total radiation. And the difference between total and direct is the diffuse radiation. And then an idealized, a little bit ad hoc SAI scenario to start with. It's a pseudo SAI approach, as Jim Hurrell put it yesterday. So it's the same methodology. There is no change in circulation or cloudiness, but we reduce the total radiation by 2% throughout the day. And we reduce the direct radiation a lot more, by 3 times that amount. And of course, we make sure that direct radiation cannot go negative. So the total radiation is reduced by 2%, that's by construction, and the direct radiation is reduced by 11.6% in this scenario. Next. Then we can start to optimize the system. So looking at the first configuration with the south-facing fixed panels, we consider 2 limit cases. The first case is where the cost panels is very high, so there is no other cost. And then the optimum would be to have very sparse panels, so a GCR that is tending to 0. So there is no shading effect at all because there is no cost on the lawn, so you can space the panels as you want. And the optimal tilt would be 27 degrees. The other limit case is where the ground costs are larger than any other cost, and then you would put as many panels as possible, and they would be laying flat. But of course, the reality is between these 2 cases where you have a mix of cost from the land and from the panels, in which case you can do your optimization, which is shown on the right side, and you see a pretty shallow minimum with an optimum GCR of about 0.5 to 0.7 on a tilt between 15 and 20 degrees, which is more or less what you can see on the picture. So that seems to be realistic. Next slide. For the east-west panels, the optimum is, of course, to have the panels flat and packed as much as possible. And the only reason you have them not horizontal is because you want the rain to evacuate from the panels. But say it's a very low tilt and a high GCR. And for the horizontal axis panels, then there is also an optimum for a GCR of 0.6 with a nice minimum. Next. Now you can look at the 2 scenarios. So we have one scenario without SAI, so that's the present day, and we find some optimum value for these scenarios. And then we have a pseudo SAI scenario. And first, if we don't optimize, we don't re-optimize, we just use the same configuration done for the present day, then you see that the cost of these panels is increasing, but it's not increasing much. That's the numbers in parentheses on the right-hand side column. So for the first configuration, the cost is increasing by 2.8%, 1.8% for east-west panels, and 3.2% for the horizontal axis panels. So it's more than the 2% decrease in radiation, but it's far less than the 11% decrease in total radiation. And for the east-west panels, it's even less than the 2% because the east-west panels are pretty good at capturing the diffuse radiation. So they do a good job under a sky with more aerosols. And then if you re-optimize the system to account for the change in radiation, then you can gain a little. For the first and the third configuration, you see that you can decrease the increasing cost by about 10%. Next slide. So that's about all I had. Of course, this is a very simple SAI scenario. So we need now to work with a much more realistic SAI scenario with direct and diffuse radiation changes, and also accounting for that in the real world, it's even more complex. Even for we've made a step change in the complexity, it's even more complex. Next slide, and just wanted to finish by thanking the ESA, European Space Agency, for their support.
Thank you very much. And this concludes all the speakers of this session. Thank you very much. And we'll go over to the discussion. Please place any questions in the chat. And if you are a panelist, also you can raise your hand. You can also place questions, the Q&A in the chat. So far I don't see any. If anybody sees it, let me know. I guess I can have a question quickly. One is to Olivier. I don't know. You mentioned that the temperature effect of SAI wasn't included in your study. Is that right? That basically the cooling of SAI also has an effect because at least from my understanding and experience owning solar panels, cooler seasons produce much more than if it's really hot.
Yes, you're absolutely right. And this effect was in the previous 2 studies. So it's just a lack of time. I didn't include it. But yes, with colder temperature, you would generally increase the efficiency of the panel, especially in hot regions. So that would diminish the increase in cost that I've shown.
Yeah. Okay, thanks. Other questions? The floor is open. There is a question by Doug. Please go ahead and unmute.
I guess if nobody else has a question, I can ask this, which is that assume you account for the diffuse radiation goes up, which means that it spreads the power out over a larger fraction of the day, which might make it more expensive per kilowatt hour produced, but it might make the overall system cost actually go down rather than up.
Yes, you're right. So as the direct radiation reduces more than the total, that means the diffuse radiation goes up. So we account for that. And my last slide went very quickly, but I had indeed a note that that wasn't the end of the story, because then you want to optimize an economical system where you need to give value to the electricity, and that value changes during the time of the day. And then comes into the picture, the storage, and how much storage you need to put, and so on and so forth. So I think that the optimization, which at the moment is purely a sort of a geometrical optimization, helps with SAI, but if we had the full system, it would help further.
Great. Sorry, I missed that on the last slide.
Yeah, I went too quickly, but yeah, with a note.
Thank you. Are there more questions? Well, I guess I could think of more questions, but we also actually right at the end of our time, and we do have more discussions in the next coming day. So if there are no questions, I give this further to Mark now for some concluding remarks, if there are any, and else thank you very much, all of you, for joining.
Yeah, thank you, Simone, and all of the speakers. I don't really want to say much, and our next session is tomorrow, and that's from 9 to 12 UTC, so bit of not so good time for the people based in North America, but more favorable for those in Europe and Asia. And hope to see many of you tomorrow, where we have fewer talks and more discussion. So look forward to seeing as many of you as possible. And with that, we close for today. So I guess you can stop the recording, and then people can start to log out. Thank you.